this morning. So there'll be plenty of time to mix it up later in the week. So you can start.
Yeah, welcome everybody, and thank you so much for coming to Boulder. You're at the WCRP ESMO Ultra High Resolution Earth System Modeling Workshop. We will kick it off with some logistics at the beginning, and then we have some overall introduction presentations. So I think, Andrew, you're giving the logistics at the beginning.
So thank you. I'm Andrew Gettleman, that's Andreas Prine, and we're both here at NCAR, and on behalf of the rest of the organizing committee, which is Kath Senior, Kathy Honiger, and Christian Jakob, welcome. Thank you for coming. And then, so I'm going to give just a brief introduction to logistics. It's great to see everybody in 3 dimensions. Thank you for coming. We're excited to welcome you to NCAR. The meeting, as you'll see, is going to be structured mostly in person. We are actually, as I'll indicate, streaming all the talks so that people can watch them online. There's not going to be interactive questions or anything like that. We do have a few remote presenters who are giving invited talks, then lots of time for in-person breakouts, and equal to this group, we have a series of online breakouts that you won't be interacting with, but they'll come back on Friday, and we'll have some summaries of those as well, just like you're going to have the summaries on Friday. So a couple of notes. You've probably noticed this morning the building doors are locked. If you get locked out, if you go outside during the break, today the weather may not be so nice by Boulder standards. Tomorrow it's supposed to be, and the rest of the week will be much better. But there is a covered cupola outside, so there's plenty of places to be outside, which is nice. If you're outside during the breaks, there'll probably be people in the lobby, but we're not going to be staffed fully with people in there. So if nobody's in there and the doors are locked, there's 2 options. Would recommend that you find a buddy, somebody from your institution or somebody you know, share cell phone numbers. So anybody can let anybody in the building. So if somebody's in this room, we just don't want somebody standing out there for 15 minutes when we could just like let them in. Or you can actually call or text myself or Andreas if you really need to get in the building and nobody can let you in. But we recommend finding a buddy and coordinating access so you can just let somebody know, hey, can you just come get me at the door? Lunch and breaks will be at this building, in this building. There's a cafeteria over there. You can sit inside, outside, or in here. Speakers need, if you're not from NCAR, we actually request that you sign just a consent form because we are recording and streaming everything and it will be available later. That's by our UCAR policy. And everybody, please, you've probably gotten your COVID certification. It's just a 1-page thing that says you're vaccinated. Those of you who came from overseas had to do this to get into the country. So remnants of COVID protocols, we still need to do this. And if you haven't done it online, you can just and send it in. You can just sign one at the lobby there. Rooms are going to be this configuration pretty much all week. We're going to end up closing this, and we'll figure out, we may slide together and just use this part. Otherwise, we'll be using basically this area for one breakout, that area for another breakout closed off, and then we have a seminar room right upstairs. So, and those are going to stay that way all week. What else? Oh, this isn't the version that, I think I added the Wi-Fi to this and that didn't get transferred. So Wi-Fi access, if you haven't figured it out, there's 2 options for you. One is EduRoam. If you have EduRoam certificates, that should work. I know it's worked for a number of people this morning. If not, there is a UCAR visitor wireless network, and you can just log into that. That should be pretty open. I think you have to, I don't even know if you have to click on something anymore. I think that's it. If there's other questions, please about logistics, please ask Andreas or I if there's anything. The bathrooms are back over there on that side of the hallway, around the hallway there. I think that's it. Speaker notes, as I said, we're streaming and recording. Presentations are going to be presented from here. So there's a nice little clicker, so you can go backwards and forwards. And there is a top little red button, which is a laser pointer. So we are going to use this. Keep in mind, if you do that too extensively, it'll be a problem for the people who are trying to watch the talks later. But we don't have a way to do the pointer here. So if you want to demonstrate, just go ahead and do it. And this is pretty easy. There's not a lot of extra buttons, and I think the system should work pretty well. So because we're doing that, please email or hand your presentation to either myself or Andreas. And please try to do that at least one session before so that we're not scrambling to try to get everything together. And we're happy to check things for people and just make sure it works. We can convert. I've been converting a couple of keynote talks to PowerPoint. It has to be PowerPoint or PDF for the system we're using. And I think that's it. Oh, breakout sessions. So if you're a moderator from the breakout sessions, please meet the organizers today for lunch. We'll have a few items for you and just help answer questions in advance. And then those will start this afternoon. There'll be a little bit of introduction. Logistics, there's 3 different rooms. As I mentioned, we'll go over that again. And the assignments were sent to you. Otherwise, they're on the board outside, the information board. There's 1, 2, and 3, and you can find your name there. And those have been posted. And those will be the same groups all week. So hopefully you'll get used to it. And then for Friday, just encouragement to please stay Friday morning. And if anybody needs a ride to the airport on Friday in the afternoon, please let us know. Andreas and I can try to coordinate. There is a bus. It's not the easiest thing in the world. We can point you to that. There's also shuttles, and there's sort of Uber and Lyft, shared rides. If we get enough people together, we could actually order shuttles, and that would be sort of cheaper and faster for people. I think that's it. Also, the breakout should be, I think there's a lot of good talks. The talks look fantastic. The people here are fantastic. So I'm going to encourage the local people. You might want to stick around because you're probably going to learn something, not as much if you go back to your office and go sit on Zoom all week. Just saying, you can do that next week. So encouragement for all my colleagues here at NCAR to stay. You can also Zoom from here if you want and then come back in when it's interesting. So I think that's it for me. Oh, UCAR Code of Conduct. We'd like this obviously to be a respectful meeting, so that means be respectful to each other, usual things of sharing the air, offering constructive feedback, acknowledging and showing appreciation for people, and being open to consider new ideas, which is all the things that we stand for here. And that's it. So next is Kath to take us off on a tag team presentation for introductions, programmatic introductions.
So this will go forward, will it? Yeah, okay. Okay, so hi, I'm Kath Senior. I'm at the UK Met Office, and I'm here as co-chair of the new core project under WCRP, ESMO, Earth System Modeling and Observations. So I'm going to start by just giving you a little bit of background about that. ESMO is one of the sponsors for this workshop, and we're working together with the Lighthouse activity Digital Earth that Christian's going to talk about in a minute. So just want to start by huge thanks to Andrew and Andy Prine, who have really pulled together everything here in terms of the logistics for this workshop. I think it's going to be a fantastic week, and it's just really nice to see everybody in person and be able to have proper breakout groups where we could actually talk and think about these topics. So ESMO, you may or may not have heard of it. As I say, it's a new WCRP core project, and myself and Susan Tegmeyer have been acting as interim co-chairs for about the last year since it kicked off. So we were part of the kind of restructure, if you like, of WCRP. So those of you who know and love the WCRP will be aware of the very long-standing core projects, CLIC, GWEX, Spark, and CLIVAR. And so under this restructure, we now have 2 new WCRP core projects called ESMO and RIFS, Regional Information for Societies. And the idea, I think, really was partly to simplify the very complex WCRP structure, but also to bring together a lot of the working groups that kind of sat in a sort of satellite space, if you like, and really promote them to have the same kind of level of standing as the existing core projects. So the new structure really is organized around these 6 core projects. We also have new activities, these so-called lighthouse activities. So people will be familiar with the long-standing grand challenges that we had in WCRP. Those have now been sunset. I think sunsetting is a WCRP word, right? I've never ever heard that before, but they are now fading into the distance and have been taken on really by these lighthouse activities. And these are activities that are kind of pump priming type activities, really giving some new energy to particular topics that need initial strong focus, lasting for a few years, and then being absorbed, I guess, into the wider structure. So the way that the core projects and the lighthouse activities kind of sit is sort of illustrated here. So ESMO is really an underpinning activity working on all things Earth system modelling and observations. Then the 4 existing core projects sit in the middle, if you like, and they work. Obviously, many of the activities that happen in these core projects are around Earth system modelling and observations, but perhaps a more deeper dive and not really representing the tools as much as we are in ESMO. And then RIFS is a more, as its name suggests, more outward-looking, interacting with society, particularly on kind of regional scales. And the lighthouse activities illustrated here, again, work very much in combination with the core projects and picking particular activities that need to be promoted at that particular time. And Digital Earth, obviously, is one of those. So this is ESMO. We have written a sort of draft strategy. It's based around kind of 3 scientific objectives that we hope will be kind of set the scene, I guess, for this over the next decade of climate modelling, data assimilation and observations activities. So we're working on advancing, predicting and projecting the Earth system. We're looking to improve our monitoring and understanding of Earth system change, and we want to harness and advance emerging technologies on modelling and observations. So these are incredibly broad. We recognise, I think, there's going to be a number of cross-cutting themes, and in particular at the moment we're focused on the carbon cycle as one of those that sits directly under ESMO, that integrates across these 3 priority areas, and also extremes. But there will be others as we go through time and sort of look to pick out what we can promote within ESMO. So the idea is that these are informed by some of the most pressing shortcomings in our ability in these areas, and to advance the core capabilities of the WCRP programme. So obviously, as I've said, Earth system modelling and observations underpins everything in WCRP, and if we're not trying to suck everything into ESMO by any stretch of the imagination, we recognise there's a lot of overlap with the core projects, with the lighthouse activities, and our work is really to support where that expertise exists and work to coordinate and bring it together. So our focus will be on picking those priority topics where we think coordination can help, and where there's the potential for strong collaboration across the activities, and where we can promote more rapid results and benefits. And of course, this kilometre scale modelling is absolutely one of our priority topics, as it is with Digital Earth. And so this workshop, I think, represents an example of the sort of thing that we're trying to do in ESMO. So finally, just for those who perhaps know a little bit more about the previous structure of WCRP and how does ESMO work, we are pulling together in this kind of red box at the bottom all of these working groups, so those that we know and love, WGCM, WIGNI, WGCIP. We're looking to initiate perhaps some new working groups, particularly in the observational area where there's fewer. We will have a relatively small steering committee that will sit over the top of these working groups and work very closely with the co-chairs of the working groups. And together those 2 communities will look to look at what are the priorities for ESMO, what are the activities that we can coordinate better across the working groups, what should we be focusing on. And of course also a recognition that we need in this activity to work very strongly with groups in the other core projects that have modelling and observations at their heart. So OMDP in CLIVAR would be one, CORDEX that now sits in RIFS would be another. So it's not that ESMO has everything to do with modelling and observations in it. It clearly doesn't, and we need to maintain these interactions. So that's a very quick overview of what ESMO is trying to do. And as I say, this workshop, I think, represents one of our first activities, trying to work alongside one of the Lighthouse activities, in this case Digital Earth, on topics of clear joint interest. So I hope the next slide, will be Christian's, and I'll hand over to him.
We are hopelessly ahead of time, aren't we? And this is where online stuff really gets you, doesn't it? Because the online people who want to see Kathy's talk won't log in until whatever we said we would be starting it at, whereas. So we might have to take a break earlier. So first of all, like Andrew and Kath have already said, thank you very much for coming to this workshop. I want to impress on you that this is probably going to be a pretty historic workshop. It's historic for many reasons. The first reason is it's probably for many of you the first workshop you've been to in 3 dimensions in a long, long time. It certainly is for me. And so, you know, embrace that piece of history we are making today, right? We're for the first time after post-COVID, we are back in person. The second reason it could be historic is the topic we are here to talk about is a relatively new but very fashionable topic. It's, you know, high resolution modeling, kilometer scale modeling, global kilometer scale modeling. It's also a very controversial topic if you follow blogs and Twitter spheres, which I don't, for reasons that I will explain to you over beer if you want. You will realize this is actually quite a hot topic, and it's an exciting topic. And this is kind of the scene-setting workshop for the international coordination of kilometer scale modeling. There are smaller projects in particular spheres out, like the Diamond project, which is largely focused still on the atmosphere. But in a sort of coupled modeling sense, there has been no sort of international idea on how we want to collaborate internationally, and also how we want to push this field forward. And you, especially through the breakout group discussions, will have a large influence what happens over the next 5 years in this area on the international scene. Now, if you're scared by that, you can always skip and go into the lovely town of Boulder and have coffees, but I encourage you not to do that and actually come and help us set the scene. Because if you don't, then it's going to be people like Andrew and I who will do it, and I bet you don't want that. The other thing that's historic about this, that we're trying to achieve with this, before I get into explaining Digital Earth a little bit better, is we see, for the first time, as far as I can remember, and I've been in modeling for 30 years, an opportunity to bring new communities together, in particular to cross the divide between global and regional modeling. Having this kilometer scale focus in both communities, we see as a great opportunity to bring those 2 communities together. And I hope the reaction of the regional community to kilometer scale global modeling isn't, okay, then we'll run ahead and do 100 meters, blah, we won't work with you. I'd rather have us use this opportunity that we're all working on similar scales to come together. Anyway, the vehicle that the World Climate Research Program has chosen to try and do this is called the Digital Earth Lighthouse Activity. This workshop's mostly going to be about science, but we can't avoid that if we want to get together internationally, we have to find ourselves a structure that we all like and that actually adds value to what's already happening. So that's why we're here, trying to figure out how can we add value to what people are already doing in this space anyway, through international activities. So am I meant to click on this forward? Because it's not obeying my command. Now it is. So the WCRP has several of these lighthouse activities. I don't want to bore you too much with organizational stuff. Suffice to say, the Digital Earth Lighthouse activity is one of 5, and they are meant to be sort of cross-cutting activities that push new areas in our field. And so what's the Digital Earth want to push? Push? Talking about push? I have to point it this way? That way? That way? I'm lost. Oh, it's happened. When you read this sentence, it makes no sense, so don't read it. And you can tell it's been written by a jet-lagged person. But it's sort of right. So what's the goal of this Digital Earth Lighthouse? So the big vision is that instead of having all these different models and data in formats that are pretty alien to users, somewhere stored like we've done for the past 3 to 4 decades, that we envisage that the future of our field interacting with the rest of the world are digital information systems, where people go and literally on their iPhone can get information about the past, the present, and the future of the Earth. And that's, when you express that vision to people, then most people say, that's just a pipe dream, go away. But bear with me for a second, just keep it in the back of your mind. Wouldn't it be nice if we had it, right? And if we agree that it would be nice that we had it, then we might want to say, well, where would we start making it? Where would we start building it? And so we really want to think that people don't actually care about temperature and rainfall, but they care about what it does to things. They care about what it does to their crops. They care about wind, not because it's windy. They care about wind because it either destroys things, or most importantly, it will make a lot of our electricity a few decades from now. So wind is not, we as meteorologists or oceanographers think of our variables in a scientific sense, but really people care about them for reasons. And wouldn't it be nice if we could integrate our scientific interest in the wind with the societal interest in the wind and actually build systems where we can predict this days, weeks, months, centuries ahead and project it into the future under scenarios. And really to the person on the ground who wants to know about wind power, it all comes from a simple to interact with information system. So there's a lot of work. We are miles and miles and miles away from this. There's no doubt. So how would we do that? So that's the overall vision of the Digital Earth Lighthouse. To do this, we've identified that we need major activity, not just a little bit of activity, in 3 major areas. One is the one you hear about this week, which is fully coupled kilometer-scale regional and global models. To do that, we really need to build a global network of researchers with expertise in this space. And this is almost, it's Earth system modeling on steroids. That's how I often like to describe it. And how would we do that? The second thing we need to know, if we're talking about past, present, and future, we need to know what the system is like at any given point in time right now. We need a description of the system. And not just for initial conditions, but also for studying the past, looking at people making decisions on the now, not just on the future. That requires our data assimilation systems, the things that most of you experience through reanalyses, to be actually designed to be data assimilation systems for climate, which most of them are not. They're data assimilation systems to make good initial conditions, to make forecasts. They're not necessarily the best systems to describe the state of the system. Very few of them conserve lovely things like energy, water, and momentum, for example. Now, as a climate person, that's abhorrent. You cannot do climate analysis with a budget that doesn't close. It just makes it very hard. Mind you, observational budgets hardly ever close either, so it's an issue. So that's the second activity, and Anish, I think he's in the room back there, is leading this activity for us. And then the third activity is we want to build an information system that talks about crops and wind power and whatnot. Earth system models are not going to cut it. We actually need to integrate prediction systems for these types of impacts, for lack of a better word. And that's also a very challenging thing to do. And we need to integrate them not just conceptually and scientifically, we need to integrate them technically as well. We actually need to have them built somehow into our information system. But this week is about the first of those 3. It's about building kilometer-scale regional and global models. So I have some thoughts I want to share with you before I hand over back to Andrew to talk about our specific goals for this workshop. But these thoughts are feeding into these workshop goals quite strongly. So after a lot of thought and amongst the people who are meant to lead this activity, we've come to the conclusion that we think, and you may tell us we are off our rockers thinking that this week, we think that the biggest value we can add is to create a home for the development community of these 3 types of systems that I've been talking about. There's lots and lots of activity in the application of climate information and so on going on already. There's usually, and this is an old hobby horse, and I have a bee in my bonnet, and all these things apply to this statement, is the model development community is usually not very well supported. And so we think that this Digital Earth Lighthouse activity could become the home for the development community of kilometer scale models, data assimilation systems for climate, and information system components that integrate. To do this, we have the desire to create some fora in which people can come together on a regular basis to discuss issues. And we really want to go away from the propaganda to the science. The best workshops you can have are the ones where people talk about what doesn't work. And we haven't got enough workshops, especially in this kilometer scale modeling area that I've seen, that do that. Let's talk about what doesn't work and how we can make it better. So please keep that in mind for this week. Please show us your dirty laundry. Don't give us the propaganda speeches. We've heard them all. We know. Thank you. Let's move on and talk about how we're actually going to do it and what are the stumbling blocks. Where are we worried? What doesn't work? And so we want to create some fora, and we need your input on what they might look like. The WCRP often has working groups, and some of them have been very successful. Kath was telling you about the working group on coupled modeling, whose absolute star project is CMIP, and I think you all know about CMIP. So how do we want to organize the kilometer scale modeling community to have a similar forum where they can come together and share experiences? And the last thing I want you to think about this week is to create practical activities. It's nice and fine to stand on a podium like I do right now and pontificate about this, that, and the other, but at the end of the day, progress comes from doing things. And if we are an international community, it's about doing them together. So what are the things we could do together that would progress this field more than if everybody does them by themselves? So that's where I hand over to Andrew to talk about some of the goals we have for this week specifically. Thank you. It's working now. It's working now. It's working now.
Thanks, Christian. So I'm going to take a little slightly deeper dive into that. And as Christian said, we're focusing on this one piece of the Lighthouse activity, which is the regional and global coupled scale, kilometer scale modeling. The overall goals that you've seen on the website, bringing people together, discussing the scientific and computational challenges, so talking about our dirty laundry, and how to clean it, actually, that's the other piece. Applications of kilometer scale models, we'll delve into that a little bit, although that's not the primary focus. And then sharing, again, current progress in both high resolution modeling and also in the individual spheres, as well as in coupled modeling. So there's, as Christian said, there's other efforts that people might know, such as Diamond, which have focused on one sphere. They're starting to do coupled, but they're not as comprehensive as potentially they could be. And so where can we help build communities there? And it's identifying joint tasks and also some issues of nomenclature, what we call these models. Some of this has actually come from the atmosphere, and that may not be the most appropriate. So we'll get into that in a second. There's some things we're not going to do here. We're not going to discuss whether these models are useful or whether we should stick to standard CMIP models for our work and for applications. This is not a 100-kilometer scale modeling workshop. We can discuss similarities and differences with resolution. We can discuss when you would use models. We can discuss global versus regional. We can discuss downscaling, but we're not going to talk about the utility of operating at the kilometer scale. And we're also going to try to minimize the propaganda, as Christian said. We're happy to see some of those pretty pictures, but let's get into why the pretty pictures look great. Like, for example, this is actually from Falco. This is a Diamond model from NCAR, and it's a pretty picture. Falco will talk about all the problems with this model, but all the benefits of this model too. So we want to actually get to that level of detail. This is sort of what I keep falling back to when we think about that, and you can read it and I'll read it aloud. I don't want to go among mad people, Alice remarked. You can't help that, said the cat, and there's our Cheshire cat who keeps disappearing. We're all mad here. I'm mad, you're mad. How do you know I'm mad, asked Alice. You must be mad, said the cat, or you wouldn't have come here. So we're all here. We're all a little bit mad because we're trying to do crazy things, just like this cat, just like this image of the planet, and it's very appropriate to go back to Lewis Carroll and Alice's Adventures in Wonderland. So one of the main things, just to note, to look around you, who's here? We're trying to bring people together, and hopefully there's some familiar faces, people after 3 years that hopefully you still recognize, who you can see in 3D for the first time in a long time. But hopefully there's people that you don't recognize. I see some very old friends and colleagues, and I see some people I've never met before, which is fantastic. We have people from different spheres of the global Earth system, atmosphere, ocean, land, ice, etc. People who take different approaches, both regional and global modeling. They're different foci, people who work on physics, people who work on diagnostics, people who work on computations, dynamical cores. We're going to mix it up. And we're sort of hopefully representing a lot of other people who are not here as well and different communities. So how are we going to accomplish all these goals? Listening to each other, the standard of invited and contributed talks. There are going to be breakout group discussions. As you've seen, they're going to be focused. So same breakout group the whole week, common questions to work through, several sessions. We're collecting ideas from each breakout. And there's also going to be 3 online breakout groups for those who can't be here. They're going to address the same questions. So we're trying to make sure it's not just the people who are able to show up, because that's very limiting in this day and age, from travel restrictions to visa requirements to funding to all that stuff. We know that not everybody can be here, so we're taking advantage of the pandemic. We now know how to do this a little better, so we're having participation from multiple time zones, and that's happening mostly Wednesday and Thursday. And then Friday, we're gonna have a summary and next steps, and there will be some documentation and report. We'll have to figure out exactly what form that's going to take, at least going back up through ESMO, potentially going broader than that if we have interesting things to say that we think are useful. Again, common questions for each groups in these breakout sessions, several sessions. There will be short plenaries. We'll introduce them in a little more detail this afternoon. There'll be short plenaries Tuesday and Wednesday. If you're unsure of something or something comes up, we can discuss on Tuesday in these short plenaries. If not, we can let everybody go back to their breakout groups. We're going to collect ideas from each breakout and share documents, so you'll get a little more instructions as to that, but that hopefully will enable us to have multiple ways of communicating that everybody's comfortable with. Also, we intend these groups to be flexible. The questions are a starting point, so feel free to evolve as you learn new things, and you can add comments at any time because of these shared documents that are going to live there, and you don't have to wait till somebody calls on you in a working group, in a session. So if you're talking to other people and come up with something at the pub and want to actually come up and add notes to the document, go ahead, and you can discuss it the next day, and you can come up. So again, next steps, what can we do to accelerate and or share progress, some of the key challenges in different areas, and then focusing on what are the community efforts we can do for the next few years to really advance the field and to actually try to overcome our challenges in shared ways and get to this vision of being able to do better prediction and get it to people in the ways that they need to actually access it. So, having said that again, Friday is probably the most important day of the meeting. We're going to discuss the breakout group reports. We're going to do some synthesis as a group. There'll be a summary and work on writing a document for the WCRP and ESMO. How do we move the questions forward, basically? How do we take this to the next steps? There will be prizes on Friday if you stay. The best working group summary, there will be prizes for that. And then we do need to come up with a name for these models. We've called this kilometer scale. People may not know what that means. In the atmosphere, people have called them global storm resolving models because they're not convective resolving or cloud resolving. They're storm resolving, but storms mean different things to different people, and that may be totally irrelevant if you're working in the ocean or the land or something like that. So we need a better name. There'll be, and it has to be not a sphere-specific name, but there will be a prize for that on Friday. So hopefully it gets your creative juices flowing. I think that's about it. So I guess we can take questions on any of that if there's questions for any of us or logistical questions. So for questions, I forgot to note this earlier, we're not actually interacting online, so we don't have to worry about that, which is good. But we do have microphones, and so for organizing it and also for being able to hear everybody and hear the questions, just please come up and you can queue behind the microphones. If you don't know how to do that, you can ask somebody who comes from the UK. They're good at it. Professionals, I would say. Okay, where are we on time, Andreas? We're probably ahead of time. 10 minutes. We can just go ahead because this is, it's just, we're recording the session, it'll be streamed, it'll be put up on the internet afterwards if somebody's watching it, fine, so.
Thank you very much for the introductions, and we start off now with our first keynote speaker, who is Kathi Honegger from the Max Planck Institute in Hamburg, Germany. And she will talk about K-scale coupled modeling challenges and opportunities. The keynotes will be 45 minutes long. I will give you a sign at 30 minutes and probably get closer and closer to you as time progresses to make sure that we have some room for discussion at the end. So, Kathi.
Thank you. Thanks, Andreas, for the introduction. Yes. So let me start. So this is a nice picture. So this is a picture of a 10-meter wind. This is from a global simulation that was conducted with the ICON model with a grid spacing of 1.25 kilometers. This is a coupled simulation, and this is really the best in terms of resolution that we can do nowadays with ICON. Of course, for me, which is more also a bit from my background, so what is kind of amazing on that plot is how the continent stand out. But we can also zoom in and we can see expected the large-scale feature of the atmosphere with the front, but now we also see the small scale, like wind shadow behind island. Those are not the crater on the moon, but those are the imprint of convective cells on the wind in the tropical Pacific that we see in the simulation. And also, we also see the imprint of the small-scale orography that we can now resolve with a grid spacing of 1.25 kilometers on the wind. This is an example for the Alps. And finally, more focus on the ocean. This is now a plot of the surface temperature. This is the southern tip of Africa, and we can see the eddies in the oceans. So that was for the nice picture. And as Christian said, I'm not here to talk about nice picture, but I'm mostly to talk here about challenges and opportunities in this type of simulations. So what I wanted to do with this talk is talk about 4 different aspects. The first one I call here just setting the scene. So we're just kind of saying what type of simulation we can currently do with ICON so that we are kind of all a bit on the same page. So if someone come up with a crazy idea about running something with very fine resolution or very long time scale, this might be not as a crazy idea as some people might think. And then I will talk about 3 aspects of the simulation. So the first one is the good. So there are things that are pretty nice that we get just out of the box. But then I will spend most of the time talking about the bad, so what is not so good, and what I call the ugly, because I had to talk about good, bad, and ugly because of that movie that people probably knows. So let me start with the first, which is just setting the scene. So what can we at now really simulate with ICON S? So ICON S is ICON Sapphire, and this is the model that we are developing at the Max Planck Institute to be used at kilometer scale. And the best that we can do at the moment is really we can run the model globally in a coupled setup with a grid spacing of 1.25 kilometers, and we can do that for a few hours. And here you can see the throughput. So the throughput is 0.5 simulated day per day on 908 nodes of Levante. So the Levante is the latest supercomputer at the German Computer Climate Service Center. And this is about 1/3 of the machine. So typically, we kind of say if we want a climate simulation to be useful, this number here should be 1 simulated year per day. So here we are still far away from the target, but with more powerful machine, we could get there in the next year. Also, all the numbers that I'm kind of showing here are for CPU architectures, but we can also run ICON on GPU, and this will give us a factor of 8. Of course, we can coarsen the grid spacing, and we can do global atmosphere-ocean coupled simulation with a grid spacing of 2.5 kilometers. We have done this for a few months, and here the throughput is 20 simulated day per day on 600 nodes. We can coarsen a little bit more the grid spacing, and we can do 5 kilometers, and here we can really already do yearly simulations. And this is really a bit, at the moment, our working horse, the 5 kilometer run.
this gives us a little bit more than 100 simulated days per day. And finally, if we do 10 kilometers, we actually have been run 10 kilometers global for 30 years. And here you can see we are by this kind of magic number of 1 simulated year per day. So this is just a bit just to set the scene. So that's kind of, we can do some other configuration because we always want to have very high resolution, so even higher than 1.25 kilometer. So what we can also do with ICON is we can do a global coupled simulation where we use a uniform grid in the atmosphere, but where we use a telescoping grid in the ocean. So here, for instance, we use a 5-kilometer grid in the atmosphere, but then we have a telescoping grid in the ocean, which goes from 11 kilometers down to 530 meters in some region to get even finest resolution. Of course, we can also run ICON as atmosphere only, and we can do regional climate simulation, so there might be here a link to the regional communities. And depending on the domain size, we can go to very high resolution. We can also do ocean-only simulations, but those ones, we cannot do them on limited area domain, but we can use this kind of telescoping grid feature that I just mentioned. And finally, what we are also trying to do is, at the end, we would really like to have Earth system model simulation running at kilometer scale. And for that, we need carbon. And the first step to have carbon in the model is to be able to run ocean biogeochemistry. And we have been here doing simulation with ocean only, but including biogeochemistry with a grid spacing of 10 years. So this is just kind of setting the scene, what we can do with ICON. But now I come to the more interesting part, which is really talking about challenges and opportunity of this type of coupled kilometer scale simulation. And I start with the good. So obviously we had to look at the climate and try to figure out what aspects of the climate system are well reproduced by those simulations. And maybe not so surprisingly, but we can capture the large-scale circulation of the atmosphere. So this is just a plot which shows sea level pressure as function of the latitude. This is for DGF, this is for GGA. And I have in black the 10-year mean of the reanalysis. In blue, this is 1-year mean of the 5-kilometer coupled simulation. And then for the gray, those are individual years for the reanalysis to get a bit of an idea of the internal variability. So a bit of a difficulty with this run is most of the result that I will show is from this 5-kilometer coupled run, where we had kind of a bit more than 1 year simulation. And of course, it's a bit hard to compare to observation because we don't know which year I should compare to. So that's why sometimes I'm putting here more than just one curve to get a bit of an idea of the variability. And you can see the model is kind of reproducing the low pressure system in the pole region. We have the high, we see the movement with the season, and in general, we are more or less inside the internal variability. So that's good. We can look at the wind. This is the zonal wind. This is latitude. This is the height in pressure coordinate. The solid contours show the 10 meter per second zonal wind. The dashed one is a 20 meter second. Again, blue is the model. The gray line, again, are the individual years of the reanalysis. And you can see, again, we are mostly inside the internal variability. But if you look more closely, it seems that in the northern hemisphere during the boreal summer, we might get a bit too weak jets in the simulation. But all in all, I would say that's kind of good. Another aspect which is exceptionally good in this model in our simulation is actually rain over land. And this is a bit of surprise to me because I always thought the land is a bit of a messy thing. But the rain over land is very well captured, and also the seasonal migration of the rain over land. And this is what is shown here. On the left, this is for South America. On the right, this is for Africa. And then we try to explain what is on the plot. So the square here, those are from the simulation. They show the location of the red belt in one particular month, and they are colored by the month. So you can see the seasonal migration. For instance, here we start in January, February, then the rain belt moves kind of northward, a little bit toward the west, and here then is September, October, and then we kind of go back. So the square are for the model, the circle are from the observation, and you can see they're kind of on top of each other. So this is a remarkable argument. We can do the same for Africa, and you can see again, we see this movement of the rain belt, and it is kind of very similar both in the model with the square and in the observation with the circle. So this from the atmosphere side, two aspects which are very well captured. We also had a bit of look on the ocean side. The ocean is a bit more difficult to validate because we only have 1 year, so the ocean cannot kind of diverge too much from the initial condition in 1 year. But still, we can have a look if we don't see any obvious bias in the ocean. And actually, as I will show later, we found a lot of biases also on the ocean side through the development cycle. So here what I show is just salinity. On the left, this is the mean salinity. And this is just a check that the model is performing as we kind of expect. So the color shading shows the salinity. The red curve here shows the area where the precipitation is below evaporation by 3 millimeters per day. So we will expect that those areas where the precipitation is lower than the evaporation, those areas should be more saline. And this is also what we see. So those are mostly yellow areas, so the ocean is more saline. So this is more kind of a consistency check. On the right, you have the bias of the salinity compared to observation. And you can see that all in all, the bias is very small. There's quite some large biases over the pole. It's not so clear. These also come from the initial condition. We see larger biases at the mouth of the river flow. So this is Mississippi, this is Amazon, this is the Congo. And this is expected because in that run, we had to turn off the river discharge. And I will come back to this problem. But otherwise, the biases are very small. And if anything, they coincide with precipitation biases. So for instance, here you can see in this blue, this is too fresh. And this is also an area where we got too much rain. Over the equator, we don't have enough rain, and the ocean is also too saline. So again, there is a bit of consistency here, what's happening. We also check the transport of seawater, and this is shown in this table. So those are the main passages. These are the number for ICON. This is from observation. And if you compare the number, they are kind of similar. There are a bit larger difference here at the Drake Passage in the Florida-Bahama Strait. But all in all, we are still quite happy with those numbers. When we do this simulation, a question that people often ask is how to initialize the land. And in those simulations, actually, we didn't initialize the land. So what we do is we just take Ecmwf and we interpolate the data at initial time. And we do so because we didn't really know how to initialize the land, and we cannot really run 40 years at 5 kilometer grid spacing. So we don't initialize the land, but we do initialize the ocean. So one question is a bit, how does the land drift with time? And actually, it seems like it doesn't drift so much. So this is what I put like in the good part. So what I show here is the evolution of the soil moisture in the different layers of ICON. We have 5 layers. This is average over the northern mid-latitude. And you can see that most of the layers, except the 5 we don't see a drift after about 7 months. So here, when we are back in October, it seems that we are kind of stabilized, except in the layer 5. This is the same plot, but average over the tropics. And again, you can see the 3 layers, they are already equilibrated in this first year. And only you see a drift in the layer 4 and layer 5, where the soil moisture still keep on increasing. But maybe this indicates that we might not need too many years to get to an equilibrium soil moisture. So this was kind of a good surprise, at least for me. The last point is, of course, when we do this simulation, we keep on arguing, well, now we can look at the interaction between small scale and large scale, and also between components of the Earth system. And this is just kind of an example to show the opportunities of this simulation. And this is an example of a polar law, which is passing over North Pole. So what you can see on the left, this is the sea ice concentration. On the right, we have the sensible heat flux. On the top, this is for the 3rd of February. This is for the 6th of February. And here, with the contour, you see the sea level pressure. You can see the low is kind of traveling over the ice, the sea ice. And you can see as the low travel over the sea ice, it opens cracks in the sea ice. So those are polyneas and leads in the sea ice. And this has a big effect on the atmosphere, on the sensible heat flux. So when you don't have these polynea and leads, you have mostly negative sensible heat flux because the atmosphere is warmer than the ice. But then when we have this opening, you can see now we get the atmosphere, which sees the ocean, and we see positive and stronger heat flux from the ocean to the atmosphere. So this is not a surprise. This is what we also know from observation, but these are things that now we can really simulate, and we could be able to kind of study them with this type of simulations. So this is kind of the propaganda talk. So those are all what is good, what is nice plots. I mean, I do have to show that we get some stuff kind of correctly. I cannot only show the bad. But now I come to the other part. So what we didn't really get for free in those simulations, and what are things that this simulation might have issues. So I start with the bad. So the first one is the top of the atmosphere energy budget. So this is a plot of the top of the atmosphere energy budget over one seasonal cycle. Again, this is from the 5-kilometer coupled simulation. The black line is again the observation, the mean, the gray are the individual years, and the blue is the simulation. And you can see we are losing too much energy at the top of the atmosphere, and after 1 year, we still haven't equilibrated, so we are still too low. In mean, for this first year, the imbalance is about 4 watts per square meter in that run. So we are losing too much energy in that run. And as a consequence, we are too cold. This is also one big characteristic of the simulation. It is really cold. Well, it is cold. So this is an example of the summer temperature bias. So you can see the map. It's mostly too cold everywhere, which is consistent because we are losing too much energy. It's especially cold over the land, probably because of the small heat capacities. And in this first year, we have already a bias of 1.4 Kelvin. So obviously, this is a bit of an issue that we need to fix, and I will come back to talk about it in the ugly part, how to fix the top of the atmosphere energy budget, which is not so straightforward, actually. A big deception for me was that the rain is not so nice over the ocean. And I was really hoping, because now we can resolve everything explicitly, the convection will be nice. But if you look at the plot, this is not totally true over oceans. So this is the plot of the mean precipitation. The color shading is from the simulation, again, the 5-kilometer coupled simulation. The black control line shows the 80% percentile of the rain rate from the model, and the gray one shows the same, but from the observation. And you can see if you look over land, this is very nice. Over South America, the black and the gray line, they match. Over Africa, they match also. You can see over some of the ocean basin, this is not so bad. This is the tropical Atlantic. This is kind of nice. On the eastern side of the Pacific, this is also nice. But if you look here in the Indian Ocean and on the western side of the Pacific, this is not really good. So one big issue is that we don't get enough rain at the equator. And through this, we kind of get two bands in the simulation, which is not seen in the observation, both over the Western Pacific and also over the Indian Ocean. So this is a bit of a disappointment to me. And you can also see this problem if you compare to other models. So here I come back to this diamond initiative. So on the left, what I show here is the zonal mean of precipitation as function of latitude. The black is from observation. The gray is the ensemble mean of the storm resolving model which are participating in diamond. And note that the gray line, those are only atmosphere-only model that we are using kilometer scale grid spacing. So it's a bit of an unfair comparison because icon is coupled, so we don't give in the SST, whereas the other one, they have fixed SST. And the blue is icon. This is for the diamond winter comparison, which is January, February. This is for the diamond summer comparison, which is in August. And you can see that in general, yes, the blue line is more or less in the ensemble mean, but especially if you look in winter, here we have far too little rain over the equator. So this is again this issue that we get way too little rain here that we were seeing here at the equator, and then we get these two bands of precipitation. So this is something that somehow we will also, maybe it would be good to improve a bit on the precipitation. So those are the two kind of main aspects which kind of strike out as not being directly well captured from this type of simulations. And this led me to kind of how to fix this issue and what are kind of maybe some ugly aspects of these simulations. So the first one is how to fix the top of the atmosphere imbalance. And now this is a plot which shows the mean temperature. I know this is from a coupled simulation that we integrated at 10 kilometers. And you can see here you have the years, and you can see that because we have a negative imbalance at the top of the atmosphere, we have to cool. The problem is that after 8 years, we still haven't reached an equilibrium, and now we are very cold. So this is about 5 Kelvin too cold compared to the observations. So it's clear that we cannot really use that model version to do a long 30-year climate trend because this is way too cold. I mean, it's fine if you do a 1-year simulation, but not for a climate period simulation. So in principle, this is not an issue. We know that we have to tune the model. This is also what scarce resolution models are doing, but how can we tune the top of the atmosphere imbalance? One issue that we kind of encounter is, of course, we knew how to tune the low resolution model, but we don't really know how to tune those new models because we lost some of these tuning knobs. So many of these knobs were related to the convective parametrization, and we don't have the convective parametrization. And the other issue is that some of these knobs, they don't work the same way, so they didn't have any effect on the run. So we try a few things. So one thing at the beginning, we try to increase the ocean albedo, and because then this will go against this cooling. And this kind of work, but of course this is kind of hard to kind of justify, and we would maybe need to even increase the albedo a bit more than 0.12. So this is kind of maybe not a good way to do. What we try is we also try to reduce the cloud inhomogeneity parameter, which is a well-known knobs that we were using before with low-resolution simulation. So you make the cloud more or less transparent, and this kind of helps you to get more or less radiation leaving the system. And this didn't really work out because when we, for instance, try to make the cloud less transparent, then the cloud cover kind of increases, so then it kind of compensated, and it didn't have really any effect of the top of the atmosphere imbalance. So what we are kind of trying to do now is to tune the turbulence coefficient. So the issue is when we do this 5 kilometer simulation, actually we don't use any shallow convective parametrization. And also we use Magorinsky as a turbulence scheme, and we know that this is a little bit kind of a stretch because Magorinsky kind of assumed that most of the turbulence is explicitly resolved. So from this combination of not using a shallow convection scheme and using Magorinsky, we will expect to get too much clouds, and this is also what we have. We have a very cloudy world, we have too much cloud, and then we reflect too much radiation, and then we have the too cold world. So what we can do is we can try to tune the diffusion coefficient in the Magorinsky scheme. There is some, I mean, you can argue physically that you should do this, but the way we do this is a bit unphysically no, so we just kind of scale them. But at least what you can see is that it has a big effect. So these are just different versions of the same model version where we just scale the diffusion coefficient by a different factor. And you can see that by scaling them, we can nicely control the cloud amount. And if you can nicely control the cloud amount, this might allow us to kind of get rid of the top of the atmosphere imbalance. So I'm not saying that this is the way is maybe to do this because it's partly tuning, so it's not totally physically, but at least this seems to be a way that where we can better control the top of the atmosphere imbalance. But this is work in progress. Another actually kind of a bit kind of ugly surprise in those runs is the coupling between the ocean and atmosphere. The runs are coupled, and actually what turns out is that the atmosphere is really sensitive to the ocean, to the SST, and probably more than what we would have expected. And I would like to show this with an example. And this is an example, again, taken from the 5 kilometer coupled simulation over the tropical Atlantic. So here again, you see South America, Africa, and what I show here, this is the mean wind. And those are two simulations, simulation 1, simulation 2. And I will tell you in a second what are the differences between the two simulations. But first, I would like just to kind of show you the wind. Those are average over March to May. And you can see the trade winds in both runs. But what you should focus on is this area of the tropical Atlantic. So here you can see we get westerlies, whereas here we have easterlies in that simulation. And this is more striking if you do Hofmüller plot, actually. So on the x-axis, I have the latitude. On the y-axis, I have the time. This is simulation 1, simulation 2, era 5. And what kind of happened is when we start the simulation, we first had easterlies, as we should have in that area, and we should always mostly have easterlies. But then somehow the wind kind of reversed their direction, and then we got just westerlies from all the time on. In the second simulation, we see we have most of the time easterlies. Sometimes they switch, but then they switch back, and this is kind of closer to the observation. So why did we get this switch of the wind? So the wind reversed the direction over the tropical Atlantic, and I don't know. I don't have any answer to that. We are kind of looking at it, but it is related to the coupling between ocean and atmosphere, and especially to the SST. The worrying thing is that really the only difference between these two runs is their initial SST field, and the difference are not very big. So this is the initial SST field, simulation 1, simulation 2, so this is the surface temperature. And first, if you look at those two maps, we start looking at the difference on the right. The SST seem kind of more or less the same if you just look like this. If you do the difference, you see there are differences, but they're not so big. It's maybe between -1 and +1 Kelvin. And a little bit, the second simulation was a bit warmer here on the western side of the tropical Atlantic. But I would say those were not really big difference in SST, and somehow they coupled with the atmosphere, and they made the wind to reverse and to say kind of spuriously, to get spuriously westerlies over the tropical Atlantic. So this is a bit of a kind of struggle for the model, and it's a bit of an issue if the atmosphere is so sensitive to this kind of small difference in SST. And it has effect also on the rain belt. And this is a plot of the difference in precipitation between the simulation and the iMerge. So on the left is for the first simulation where we had this reversal of the wind, so going from easterly to westerly. The second one with the more realistic easterly winds. And you can see in the first case, the rain belt doesn't propagate far enough towards the north with time. So we get too little precipitation north of the equator. And again, those are really small SST different, and initial time would kind of have a big effect on the rain belt over the tropical Atlantic. What you can also see here is if you look over land, over Africa or South America, and if you compare the two simulations, the rains seem pretty similar. So actually, what we also notice is during the development cycle is land precipitation is quite robust to change that we made in the model code, whereas somehow over ocean, the rain is very sensitive to whatever we change. This issue might be related to ocean vertical mixing, and this is illustrated here on the left. So what we can see here is the ocean mixed layer depth over the tropical Atlantic. This is for ocean-only simulation with 40-kilometer grid spacing and 5-kilometer grid spacing. And you can see that as we get the grids, as we have a final grid spacing, we get a shallower mixed layer depth. And note that those two simulations, they use exactly the same setting, so we don't change anything. And you can also see here in the difference, so with the higher resolution, we get two shallow mixed layer depths. This is again saying that when we do this now high resolution simulation, we also need to think a bit how we do the ocean mixing. So here we just kind of did the approach. We took the coarse resolution setting, we applied them at high resolution, and we see what happened. And obviously here, there might be some issue with the ocean mixing. This is further shown here. Those are again plot of the mixed layer depths. The two upper row are for the phasor model. The two bottom one are from NICAM. And here, the first three columns are using the TKE mixing scheme in the ocean with different mixing parameter. This is using a different mixing scheme in the ocean, KPP. This is the ocean mixed layer depth. Those are the difference to observation. And you can see that we have still quite some big differences to observation. If you look at ICON, here this is way too shallow, again over the tropical Atlantic. And you can see that kind of changing the parameter value, it has an effect, but obviously we don't really have a configuration where the differences to observation are kind of smaller. So these are also kind of work in progress and things that maybe need more investigation. One other aspect that we didn't really think about when we started doing this simulation, and I've put again in this ugly part, is river discharge. So what we do again is we just take the coarse resolution model, we run it at high resolution, and what we did at coarse resolution was we put all the discharge of the river into one grid box. So the Amazon, we put all its water into one ocean cell, which is perfectly fine if we have a grid spacing of 100 kilometers, but not at 5 kilometers. And what happened, you can see here on the left, this is just an example of the temperature as function of time for 2 grid points. The blue one is an ocean grid point. The red one is an ocean grid point where we were kind of dumping the water from the Amazon into the ocean. And since we were dumping all the water of the Amazon into one ocean grid cell, this grid cell had to warm a lot, and it warmed by more than 70 degrees Celsius. So we have temperature of more than 70 degrees. So obviously this doesn't work, and one solution is to try to dump the river into more grid cells. How to really do this properly is not so clear, but you can see here now we dump the river discharge into more than one grid cell, and this kind of partly alleviate this problem. But again, this is a problem that we didn't really think about before doing this simulation. The last one, obviously is more on the technical side, is on the output, and this is kind of well known, but I would just kind of remind this here. So there are two issues with the output, is really how much do we write out, and actually we try to not write too much out, but still this is quite a lot. So for the 5-kilometer simulation, we are writing out 20 terabytes per month. For the 2.5 kilometer, this number kind of went up to 135 terabytes per month. Obviously, we cannot do a 30-year simulation with this type of numbers. The second issue is not only how much we write out, but how long does it take to make a plot. I don't like to wait 20 minutes to make a plot, but this is what was happening before. So this is just an example. So let's say we just want to plot a time series average over a certain area of the globe. And the way we were doing it is the way we have always do this. So we just load all the data into whatever NCL pattern, and then we just do the mean over that area, and we do the plot. The problem is if you do this, and we just use one node, then it takes 20 minutes to do the plot, because you add all this data, which have so many grid cells. Of course, you can parallelize this, and then it's a bit faster. Then you only have to wait 3 minutes and 30 seconds. So it's a bit better, but still it's kind of long. Now we have been kind of trying to do the output a bit differently, which is instead of dumping everything, all the grid cell in one NetDF file, we try to kind of dump the data into kind of subregions, so that when we do a plot, you just have to access specific files and not all the files. And in principle, this is kind of promising, because now you can see that if I want to do the same plot, and even if I only use one node, it only takes me 6.8 seconds to do the plot. And it doesn't scale so much anymore, because you anyway don't access too many data, but still you are by 5 seconds instead of 3 minutes and 30 seconds. So again, this is just kind of to illustrate that depending on how we do the output, we can do many things which make your life more complicated. So with that, I'm kind of coming at the end of my talk. I just have 2 more slides. The one is kind of a summary of our development cycle. So this is just an overview of all the different, or not all, but the major simulation we did through the development cycles. Again, to illustrate a little bit the points where we kind of struggle with those simulations and kind of the things that we discover, oh, that doesn't work, and we have to kind of try to fix them. And this is about more or less, I guess, a 2 years time frame. And we started with a simulation, which we call DPP16. And in that one, we had the albedo of 0.12 to avoid this kind of having a too low temperature. But then we look at that run, and we have unrealistic relative humidity. Actually, the atmosphere was way too moist. We have issue with the wind coupling. We didn't have any hurricanes in that run. And also, we still have the issue that we have this top of the atmosphere imbalance. So we try to fix those issues. We fixed the relative humidity by using a new turbulence scheme. There was actually a bug in the old one that we discovered after one. We fixed the wind coupling because we had a bug in the coupling between the atmosphere and the ocean. This was also present in the low resolution simulation, but not visible there. And then to tune the energy, we changed back the albedo to 0.07, but we increased this inhomogeneity parameter. Then we say, well, now we want a different coordinate in the ocean. We did the land update. We look at the run, and we had the issue with the Amazon, so we turned off the discharge, and this gave us a run which we call DPP52. We look at the run, and we mostly saw, well, we have very weird ocean current and very weird wind in that run. So we again had bugs in the model, and we have to fix this ocean bug. Still, we hadn't fixed the discharge, and this led us to DPP66. And this was mostly the run I was showing throughout this talk. Now we were there, and we kind of decided to change the radiation scheme. We also try to tune the TKE in the ocean. We try to use a new ocean spin-up. These give us to this new run, which is now called NGC 0.001. And again, we look at the run, and again, issue the wind. We have a lot of issue with the wind, it seems, over the ocean. And we got this produced westerly in the trades. Again, we try to fix this, and we fixed it by doing another new ocean spin-up. In the meantime, we kind of fixed the issue with the discharge, so we turn on the discharge, and this is NGC 6. If you look at the run, we still have the issue with the energy, so the model being too cold. We try to tune this by changing again this inhomogeneity parameter, which doesn't totally help us, but this gave us the latest run, which is called NGC 0.009. If you look at this run, the main issue that we still have is we still need to tune the energy, so the model is too cold. We still have the top of the atmosphere imbalance. We actually have an energy leak, which I didn't talk about because this is a feature of ICON, but we are losing energy. We are trying to rewrite the land-atmosphere coupling to make it easier to use, and it would be nice to fix the missing issue in the ocean. So there's still quite an open issue that we need to work on. With that, I would like to come to the overall conclusion of the talk. So as I said, I think there were kind of good surprises, there were bad surprises, and there are aspects that kind of need revision for the kilometer scale grid spacing that now we are kind of trying to patch, and maybe there we need maybe some more input how to best do this. So the good surprises, especially for me, were really the precipitation over land is really, really good, and it is really robust to model changes for some unknown reasons, but this is kind of nice. Also, it seemed that maybe the soil moisture initialization is not as critical as maybe we have been seeking before. And as I showed, some aspects of the climate system were also very well reproducing, like the large-scale atmospheric circulation, salinity in the ocean, circulation in the ocean. We had bad surprises. The really bad surprises for me was the ITCC over the Indo-Ocean and the Western Pacific, which is really not good. And also it seemed that the atmosphere is overly sensitive to the SST, which make it hard to understand what is going wrong, because from the atmosphere point of view, I'm blaming the ocean people, that they have the wrong mixing or the wrong initial SST, and the ocean people are blaming the atmosphere that we have too much cloud, so what can they do? So this is a bit complicated issues. The revision that we need for kilometer scale resolution, the key points that we learned from this simulation, we need to tune the top of the atmosphere imbalance. This is not a surprise, but somehow we need to tune it differently than what we did before. We had to think about the river discharge, and as I said, the mixing in the ocean might be something that we need to work a bit on. And with that, I thank you for your attention.
So thanks, Kathy. That was great. And thanks for showing the good, the bad, and the ugly. I actually have the movie poster as an image. I'll send it to you so you can use it to illustrate future talks. Question on actually the tuning and the development cycle. How long is the development cycle? How long do you actually run the model before you say, okay, let's stop and look at it and let's do it again? How long are those?
Yes. So to answer, so the first one is the development cycle is kind of constrained. So we have this European project, which is NICAM, and we kind of make a release once per year. So this big release here, so this was, DPP 52 was the first one we did, and this was for the hackathon, which was in October, and then 6 months later on, we had the next hackathon. So this was DP 66, and then we had, so those were kind of paced by those hackathons into that project, and those hackathons are about kind of 6 months apart. How long do we do the run in the development cycle? Not so long. So really, I only here kind of put the simulation where we had at least many months, but as you can see, the number, they kind of increased by simulation time, so all the in-between were kind of short simulation. So we kind of often do like just 1 month to do, and many of these things, we kind of see them pretty quickly. So the longest one is this guy, which is 2 years.
There was no cue. I didn't know what to do. I was waiting for the cue. Really nice talk, thank you, and really interesting. I guess one specific clarification, just
Yes.
sort of 10 kilometers down to 1, you keep the convection off, deep convection off, and maybe shallow on or off the same, let's say.
So yeah, okay, I should have said it. So from the atmosphere, we only use parameterization for the radiation, for the microphysics, and for the turbulence that we do with Magorinsky. So we don't use any convective parameterization.
So I guess in any model development activity, you kind of always have to do a lot of the development work at grid scales that are not the ultimate goal because it's just too expensive, which you've touched on there. I suppose I'm wondering, do you get a sense that if you use, for example, the 5 or the 10 or a bigger, longer grid length, that some of the biases you think will, how long do you spend thinking some of those biases will persist through all the different grid lengths, and how many do you think, well, actually going to 1 kilometer might fix that one? Yeah. You know, when do you feel optimistic that it's the scales that you need?
Yes. So at least for the top of the atmosphere energy imbalance, so going to final resolution will help it. And I mean, we have seen it when I had this study where I kind of compare simulation going from 2.5 kilometer down to 80 kilometer grid spacing, but those were atmosphere only. And you can see the big thing that really changed with grid spacing is the cloud amount. So the finer the grid spacing, the less cloud you get, and that would kind of help to fix the top of the atmosphere energy imbalance because we get less cloud. So this was the main thing that kind of helped in this atmosphere-only simulation. Those were really kind of the change in the cloud. So from a conventional point of view, we don't think that we will be able to do climate simulation globally at any grid spacing finer than 1 kilometer. So I think we will be stuck, and you can make technical argument why you will really never be able to do, I don't know, a 30 years simulation with a grid spacing of 500 meters. So I think we kind of think the 1 is the best that we will be able to do, and this might help, especially for the cloud in the atmosphere. I would think it might also help for the mixing in the ocean, because you could see there was a strong sensitivity of the mixed layer depths in the ocean with grid spacing. In that case, it went in the wrong direction, because when we had the final grid spacing, then the mixed layer depths kind of get worse. But this is probably something that the ocean people might be able to comment more on this.
Thanks for a nice overview of all the interesting work going on with this icon model. And I like that you brought up near the beginning how internal variability makes it hard to compare against observations in some cases, because these are short simulations. So I was then wondering what role that might have in the bad surprise that you highlighted about the atmosphere overly sensitive to SSTs. This was a pretty big SST difference of maybe half a Kelvin SST gradient across the tropical Atlantic, which does occur during like an Atlantic Nino. And at least in some range of latitudes about the equator, this can lead to a shift towards westerly winds. So I was wondering, is this really overly sensitive if you compare to internal coupled variability?
Yes. So I don't know. We haven't checked it, so I cannot directly answer if it is really overly sensitive. It is true that what we were also thinking is like if you run longer the coupled simulation, maybe at some point it will kind of forget this kind of difference in the initial condition from the ocean part, and then we won't get this reversal of the wind over the tropical Atlantic after some time. So if you would run it maybe for 3 years, then it will get kind of to a state that the atmosphere and the ocean, they like each other and they don't have this switch back. So that could be true. Still, it's a bit of an issue because there are many aspects that we could look at. we're just using 1-year simulation. I mean, those are expensive runs, so I don't necessarily want to run maybe 5 years. And for instance, if I would like to look at the migration of the rain belts, this would be kind of nice things to look at. And there, if it really depends so much on how is the initial state of the ocean, which is also hard to get because we have to initialize also the ocean, so we do some spin up. So yes, so I agree. So maybe just by running longer the run, then we might get a better initial state, and we could just kind of start from that one, and this might solve some of our issues.
Thank you. Yeah, I think a very good categorization of these good, bad, ugly. So for me, it's surprising. For me, is you show good points. Zonal winds are very good. In NICAM, generally zonal winds are very bad. So maybe it's yes, the discussion on each model's but good points is interesting. In fact, we generally use a gravity wave tracker at kind of a 10-kilometer resolution.
Yeah.
So I guess you don't use any subgrid parameterization. So it's amazing for me.
Yeah.
So very interesting. Atmosphere overly sensitive to SST. Maybe we need to quantify this activity to compare with the observation. If you have a good idea for such, please.
Yes. Yes, so I agree. So yes, I confirm we don't use any drag parameterization. And I agree. I mean, this point that is overly sensitive, it would be nice to quantify it. And also what we haven't really done so much is, because we also did simulation with fixed SST, so it would be nice also to compare to this type of simulation. But yes, I agree.
I didn't know if I missed it, but then you mentioned here at the end that you use a spin up for the ocean. Can you say a few more words on how you initialize the ocean?
Yes, so the way we do the spin up in the ocean is we do a very long run forced by OMIP forcing using a 10-kilometer grid spacing, so over the OMIP period, and then using reanalysis, era 5 at 10 kilometer. And then we use this to do a 10 years run with the ocean with a 5-kilometer grid spacing, so 10-year, 5-kilometer forced by era 5. And then this is the initial state that we use to start the simulation. For the 2.5-kilometer run, we just interpolate the initial state from the 5-kilometer ocean-only run to 2.5, and for the 1.25, we just interpolate it again. There we don't do any more longer run.
Kathy, thank you for your talk. In Vienna, you showed some results where you had experimented with the non-local scheme in parallel to the Smagorian scheme,
yes.
Right? You didn't say anything today because you had some really weird thermodynamic profiles. So this SST sensitivity on the ocean of convection on the ocean, is it the same if you use a non-local scheme?
I will have to check that. So yeah, we have, okay, so yeah, I have to check. I don't know by heart. So yes, so we did simulation with the Smagorian scheme where those are the run I show with this kind of reversal of the wind. We also did simulation with another one radio scheme, which is the TTE scheme, which was the run we were showing in Wien. I mean, one of the reasons for this was that the TTE scheme actually, we don't get the top of the atmosphere energy imbalance when we use the TTE scheme, but this is because of compensation of modal error, because this is actually, because actually we are energy leaking in the icon, but we are just compensating error. So, yes, I will have to check back, I don't remember.
Profiles that had that weird theta E.
Yes.
Were those the Smagorinsky?
I have to check back. We can talk later.
And that's puzzling, this SST. Yeah.
Yeah, I mean, there's a big difference between the TTE and the Smagorinsky. The Smagorinsky doesn't do much mixing, so that's why we get a lot of this cloud. And actually what we found out was that the TTE, if you look at the relative humidity profile, it kind of mixes like a convection scheme.
Thanks, Kathy, for starting us off so well in this workshop. In low-resolution modeling over decades, we've built these sort of hierarchies of modeling techniques to help us understand errors in a cheaper way than running the whole model. I mean, classic example are single-column models, right? Do you see room for this? So a lot of your issues are low-cloud issues, I would say. and the low clouds are parameterized, whether you like it or not, and whether you parameterize them with a shallow convection scheme or hope that the turbulence scheme takes care of them, doesn't matter, it's still parameterized. So are there ways of investigating some of these things without having to run
Yes.
the whole thing, and what,
Yes.
what you think would be good approaches?
Yeah, so I think it depends on the bias. So I agree for the low cloud. So for instance, so to tune the top of the atmosphere imbalance, and we found, okay, we have too much cloud, and we might be tuning the diffusion coefficient. And actually, to test this, we first did kind of torus experiments. So those are small experiments over kind of a small domain, doubly periodic boundary condition, and we kind of just check, what happened if we increase the diffusion coefficient. So in that case, this works pretty well, and it was kind of, I agree, cheap. So that's a good example. Some of these other biases, for instance, the one with the wind reversal would be kind of hard to do because this is really kind of more like an horizontal issue. So, for instance, single column would not really work. The other issue that we have, maybe this is more icon specific, is we cannot really run regionally from the ocean side. So for the ocean, we always have to run the full globe, which means that the only way, if it is really a bug which is associated with the coupling, or not bug, but if those are really issues which are associated with the coupling between the atmosphere and the ocean, we always have to just per design run the full globe. And then, but there I think most of the things you could try to look at them with a good spacing of 10 kilometers, and this is cheap.
Yeah, so this speaks to, the modeling infrastructure having to allow for all these different kinds of ways of running the model. And I think that's an interesting one that will become more and more important as we go to higher and higher resolution, because it's going to be more and more expensive. So if you build these models and you have regional capability, regional coupled, but also periodic boundary condition, LES type or CIM type capabilities, they all have to be built into the same modeling infrastructure. And I don't think we haven't thought that through enough. So, yeah.
Thanks, Kathy, for a very nice overview of the good, bad, and ugly. My question is about the tropical convection. Have you looked at MJO events, even though the run is like 1 year or a short run, MJO events that propagate through the maritime continent and how well they do over the maritime continent? Because it's really interesting ocean, land, atmosphere interactions on like diurnal time scale to intraseasonal time scale.
Yes. No, we haven't looked at the MGO, but I agree that would be a nice thing to look at. So we have started by just looking at this basic feature, but yes, I agree. I know from the diamond winter comparison, there are people who are trying to look at the MGO part.
Thank you.
You have time for one more question?
Hi, Kathy. So I am just a PhD student. I've been running ROMs since my undergrad, and this is just a perspective from regional ocean system. Do you consider tides as well? And another question would be, how is the vertical resolution for the coast?
Yes. So in that model version, we don't consider tides. So we have, in principle, we could consider tides. So we have parameterization for tides in ICON, but we don't consider them in that model version. In the DPP66, so in most of the results that I was showing, the first layer is 2 meters in the ocean. Yes, and one reason why we were using the Z-star coordinate that we implement at some point is because we wanted to use a much thinner layer. So we have been doing an experiment on kind of shorter time scale using kind of 50 centimeters in the first layer to get kind of this diurnal warming of the SST. But for those one, it's 2 meters.
I'm sorry. So actually for my undergrad, I ran ROMs for the Amazon River plume, and like what we noticed is that like once we changed the vertical layers, the depth of sorry, I'm just nervous, too many important people here, but like once we changed the resolution of the vertical layers, like that changed a lot how the Amazon River plume moved around like the coast. So I don't know, just I thought about it.
Yeah. No, I think that's a good point that we should also keep in mind that this will have an effect. And actually one reason we don't use so so thin layer in those runs is that we try to use this thin layer in this run, and then we get a very warm SST, which might be related again to the mixing, so that's why we kind of keep a bit coarser vertical resolution in that run. But yes, I agree.
Yeah, thank you, Kathy, and let's thank Kathy again. And can keep on the discussion into the coffee break. Back at 11, yeah. side is compostable. So please compost everything that you use. And the other update is we will seal off this wall, and I will ask everybody that sits in the northern bay to bring their stuff over during the lunch break or before the lunch break. We will use this room for breakout sessions later on. So we will put a few more tables over here, and there should be plenty of space. Okay, with that, I'm welcoming Nicolina Bunn from the University of Innsbruck in Austria. And Nicolina will talk about regional kilometer scale models and how to produce climate change scenarios. Stage is yours, Nicolina.
Thanks a lot, and thanks a lot for having me here. I just took the peppermint before, which was not a good thing to do, so I hope it doesn't interrupt me a lot. Yeah, thanks a lot for having me here and to give me the opportunity to talk about progress and challenges on making regional climate change simulations at the kilometer scale. And here in this talk, I will actually kind of focus on these different simulations done in an ensemble kind of setup. Now, I go here into the early years of the last decade, and this is where the first high-resolution regional climate simulation started to emerge. And I think, I also do not have to kind of motivate this community here. Why do we want to go to the high-resolution simulations here? But I mean, I want to underline again that this kind of grid spacing, we can actually switch off convective parameterizations. And at that time, this kind of approach was largely used in numerical weather prediction mode, but then, as I said, it started kind of to emerge also for the climate simulations. So we have many different studies which were done over different regions, for example, over the UK, then over the European Alps, kind of from the evaluation point of view, and then also as a climate change projections. And then, of course, also we had a review on the regional climate convection permitting modeling, which kind of summarized all this study up to now. But I mean, as I said, these were all done with different models, different regions, so there was no kind of any robust results, and we didn't know if these differences are coming from different models and different regions. So this is where these Cordex flagship pilot studies started to kind of come in, and the first one was actually on the convection phenomena at high resolution over the Alps and the Mediterranean, which was led by Erika Coppola and Stefan Sobolovsky, and it started in 2016. The main aim of that FPS was to investigate convective scale events, their processes and changes using these high-resolution simulations, provide collective assessment of our modeling capacity at the kilometer scale resolution, and shape a coherent and collective assessment of the consequences of climate change on convective event impacts at the local to regional scales. Now, this FPS was also supported by the European Climate Projections project, which was Horizon 2020 project, and there was one of the working packages, that was the working package 3, which was also dealing with the high-resolution climate simulations for Alpine and for other European regions. And I will show that later as well. But first, I want to focus here on the Alpine scale, because this was one of the mandatory domain of this FPS. So this is the domain that all groups that have participated in these experiments had to do. And we kind of did the typical or the standard downscaling approach. So we started from area interim reanalysis or some GCM data. We went to the 12 or 15 kilometer intermediate domain. So depending on which model groups we're using. So this one was using the parameterized convection, and then to 2 to 3 kilometers greater alpine region, where this parameterization of deep convection was switched off. Now the exact grid spacing was not set off, and different groups could choose which grid spacing they want to use, and this was ranging from 2.2 to 3 kilometers. There were different experiments that were done. So here we have 3 case studies. So this was kind of in the first stage. And these are the results published in the paper by Erika Coppola in 2020. And then we had the ERA interim evaluation run, which kind of included the minimum time period of 2000 to 2009. Some of the groups also went beyond that, but that was kind of the minimum to provide the data. And then we had also the downscaling of CMIP5 simulations, and here we did a historical and near future and far future simulations, and here also the periods which kind of indicate for which periods these simulations are done. Now, here I also list these different groups and different models that were conducting these simulations, and also you can see here on the side, like what grid spacing they were using, also what they were using for the intermediate step. Now in total here we had 23 simulations which had around 3 kilometer grid spacing, and 22 simulations with larger than 12 kilometer grid spacing. In total, what we also had is 6 different regional climate models represented in this ensemble. Now, as you also see here, these 23 and 22 kind of differ, so it means that some of the simulations were done without intermediate grid spacing or intermediate simulations. We were kind of, for the future kind of simulations, we kind of used 2 approach, and I already mentioned one. This is the standard downscaling to the kilometer scale grid spacing, so where we use this reanalysis data. I think something, okay. Sorry. So where we are using reanalysis data to downscale it to the regional climate model at the coarser resolution, and then we go to the kilometer scale. And this is what is known as the evaluation run. And then we downscale the GCM data to produce the control or historical run in the same way. And then we also do a forced scenario run. At the end, as we said, we use this one for the evaluation, and these 2 runs for calculation of the climate change signal. Now, with this kind of approach, what we need is in total 3 runs. In such a way, we kind of capture the full climate change signal, or what some people might call full climate change signal, because you directly downscale these GCM simulations, but you also have to keep in mind that we have relatively short time periods, for example, 10-year-long simulations, so the role of decadal variability cannot be really addressed with those simulations. And then kind of a disadvantage of this approach is that we can inherit these GCM biases at the kilometer scale. And here I show you the example of a diurnal cycle of precipitation compared with the observations. And here we have 2 models. It doesn't matter which one is which now. It's just if you compare like these observations here with these model simulations, this is reanalysis driven run, you see that they are much closer these simulations are much closer to the observations. And now if you go to the GCM-driven run, the observations here are basically the same as here, just the Y label is the same. But what you see is that the precipitation is much higher in these runs. And these kind of biases tend to come from the frequency, because we see too frequent rain in these GCM-driven simulations. Now, one way to kind of overcome these GCM biases is to use these pseudo-global warming experiments, where we start again from this reanalysis-driven run to create evaluation, or in this case now this is also a control run. Then we add the climate change signal from a global climate model to a reanalysis data to create future reanalysis, and then we downscale that to get a scenario run, and now we compare these two to get climate change signal. And in such a way, we are, so basically the signal that we add has an annual cycle, latitudinal, longitudinal, and altitudinal dependency, so it varies in all different directions, and it's applied to all variables in boundary and initial conditions. So the temperature, including sea surface temperature, pressure, wind, and humidity. The advantages of this kind of approach is to avoid GCM circulation biases, to save computational resources, and to also reduce the role of interannual variations, because as we said, we only have a 10-year-long simulations. But this advantage is that it assumes that this baroclinic eddy statistics does not change much. So these are kind of these smaller scale perturbations which we do not take from GCMs. Now, comparison of standard and PGW-driven simulations actually shows that there is not much difference of these two approaches. And here you can see it for the simulation of the precipitation mean, frequency, intensity, and heavy precipitation. This set of simulation is done at a quite coarse resolution, so 50 kilometer in this case, and of course we would also have to do it at a much higher resolution as well. But I mean, this kind of indicates that this bias, or that these approaches are kind of quite similar, and these differences between PGW and the standard approach are smaller than the differences between the two different GCMs. Now we, in this ensemble of the simulations that I said or that I presented before, we have a couple of these simulations that are done with the PGW approach as well. Now, it's not yet the end of the presentation. I just want to build my summary as I show you the results and different things. So first, I start here with the model performance. And this is now first like this shiny picture where we see a clear improvement in the simulation of precipitation with a multimodal mean at higher resolution. So what we have here is a multimodal mean at the 12 kilometer, and this one here is at the 3 kilometer for the precipitation intensity, frequency, and for the heavy precipitation. And as you can see, these higher resolution models, they improve this representation of these different characteristics of precipitation. So as you can see here, and here, the intensity is quite underestimated in the coarse resolution model, and it's captured much better in the high resolution model. And here, the frequency, which is overestimated in the 12 kilometer model, especially over these mountainous regions, is now reduced in the high resolution model. And if you somehow kind of do the mean average of this bias, you get to the number that the 12 kilometer model underestimates heavy precipitation by 40%, while 3 kilometer RCM ensemble mean only by 3%. So that's, I think, kind of quite nice and shiny results, but now we come to something that is not so shiny. And here we look into the different models, different realizations of these models done by different group. So the results here, and this one here, are basically from the previous slide. So results here are for the heavy hourly precipitation in summer season. And you can see that the variability between the model is still quite large. They can produce different results, but I think overall what we can agree is that the higher resolution, so these plots here, tend to produce more intense precipitation than their driving coarse resolution models. Now, another, again, starting with the shiny results, is the diurnal cycle of summer precipitation. So this is something that we already know from before, that this diurnal cycle of precipitation is much better reproduced with the high resolution models. And here now we see it with the multimodal ensemble as well. And we see it for the mean precipitation, wet hour frequency, and heavy precipitation. It's just astonishing how these coarse resolution models do not even reproduce this diurnal cycle of heavy precipitation. But not so shiny side here is as well, because if you look into the individual models from that ensemble, you see like many different lines crossing each other. So again, we can see that this large spread exists even with the kilometer scale ensemble models. And now we wanted to kind of see how big that actually is, or does the variability between the models decrease. And here we have different indices, frequency, intensity, and heavy precipitation for different seasons. Here is for the region of Switzerland, so basically for the regions where we had this high resolution and hourly precipitation data sets. And what we now basically have here is these box plots for different indices and for different seasons, and they kind of show the biases for that. And here we also include some observational kind of range of uncertainties, and here we are, I think, kind of on the low side, because we say this is from 0 to 25%, and we know that this actually can be much larger, for example, especially in winter season, in mountainous regions, where this can reach up to 70%. Now, if we compare these results, what we can see basically is that somehow this spread between, or this variability between the model kind of starts to get reduced. So you see this reddish kind of color coming closer or narrower and closer to zero. But this is not the case for all indices, not for all regions, and not for all seasons. So it's clear there is still something that needs to be further improved. And there kind of a couple of things or questions that have to be addressed behind that. So, for example, the first one is what from that is inherited from the driving models. And we can see here also this example on the frequency, basically where we have a large spread in the high resolution models. We also have large spreads in their driving models. Then, of course, we should not forget that maybe we are not representing all the processes correctly, or maybe we are missing some of the processes even in these kilometer scale models, and this is something that we have to kind of further investigate and focus more on this process-based evaluation. And then the next one is the observational uncertainty. As I said, I mean, this can be quite large. Here is just a simple kind of indication of it, but it can go much beyond that. Now, the next thing which I want to also show you, it's not coming from this ensemble, but it's a kind of a part of it. And this is that for one of the simulation done with Cosmo, we have also data at the sub-hourly frequency, and we kind of evaluated this data against rain gauge stations in Switzerland. And here the first plot kind of shows the 1 hour percentiles, and you can see that this simulation, the Cosmos simulation at a higher resolution here is kind of underestimating this observed intensity of the precipitation. But as we go to 30 minutes percentiles and 10 minutes percentiles, so as we go towards the higher temporal frequency of this precipitation, we are getting on the other side of that curve. So at the a higher temporal frequency, this precipitation is overestimated, and we think that this is because these high resolution models tend to produce small and very intense convective cells. Now, all this analysis up to now was kind of done overall over the entire kind of domains. And we are missing kind of different regions or different kind of complexity of topography that we have below. And the results actually look quite nice despite some of the shortcomings. But I mean, we can also ask ourselves, do these kilometer scale climate models really perform better over complex topography? And to understand or to kind of get the answer to that, we started to do analysis basically by classifying these mountainous regions on ruggedness. So we basically define here the ruggedness index, which is the difference between the maximum height and the minimum height in the box of 21 by 21 kilometers centered around this eye grid point. And now with that, we define these different ranges for the ruggedness, and if we have this Ri, which is smaller than 150 meters, we define this as a flatlands. Then we have hills, which is between 150 and 300, and then the low mountains, which are 300 and 900, and the high mountains where this index is larger than 900 meters. So it basically kind of calculates how much the topography varies in that box. And here I think you cannot maybe see it that well, but these white, gray, and black contours show which of these regions corresponds to which classification. So for example, these Alps here, they belong here to the high mountains. And now we did the analysis based on that classification. And what we have next here is a precipitation distribution at as the fractional contribution of each precipitation rate. So this analysis is done or shown here for the Alpine region, but we also have done it for different regions, and the results are basically the same. And this is that the largest kind of improvements are seen for these flatlands, hills, and low mountains. But as we go towards the high mountains, so to more complex kind of terrain, this better performance is not that much visible anymore. Yeah, this is what is written here. And in addition to that, what we also kind of saw is that we have these issues like with the low-level clouds, which are basically having a different or completely opposite diurnal cycle than their driving model, and we are still trying to understand that. I didn't show this plot here, but I mean, this is something that is kind of goes also in the line with the results what Kathy has shown, but now we also see it here over the mountains. Now, of course, there kind of space to improve these kilometer scale weather and climate models, and I want to kind of highlight one of these here. And that's basically the TMEX program, which is actually working or having the goal of further improvement of these models. And basically the idea is there to develop new parameterization schemes more complex, which would be more complex and advanced, and basically not only to improve the kilometer scale models, but also to improve driving models. And the main topic of this program is this multi-scale transport and exchange processes in the atmosphere over the mountains. So it's heavily at the moment based on the observational campaign, but the idea behind is that basically over the mountainous region we have completely different these exchange processes that are happening than over the flat regions. And despite that, I mean, in this high resolution model, even though they are so much advanced, we are still using some of the basics approximations as we have over the flat regions. And this, of course, can then explain some of these biases that we also see over these high mountains. And hopefully we will be able to improve those with these new schemes. Now, intermediate goal of this program, or on our kind of side, is to use the existing kilometer scale simulations to recognize processes that are not represented well or not represented at all. So at the moment we have a lot of these simulations that are being produced but not analyzed well, or not analyzed properly at all. So we want to kind of underline that we have to kind of also use these existing simulations to see what else is kind of not represented well, or maybe what we are missing, and that can be improved further. Now this brings me to the first summary, which was on the model performance. We see that the models with the kilometer scale resolution improve representation of climate over the Alps. However, more work is needed on further improvement, especially over complex terrain. Now I come to the part with the climate change projections. And here I first start again from the ensemble simulation. So here we have 3 kilometer and the 12 kilometer ensemble mean for the mean summer precipitation. And this was kind of quite disappointing. You do all these different simulations, so much effort, so much energy is kind of spent, and then the signal that you get is basically not that big of a difference. And again, I highlight here that this is the mean precipitation, but if you go to other precipitation characteristics, so for example, the intensity, frequency, and heavy precipitation, we start to see the differences between the modeling approaches. So for example, here up, the intensity change is much is higher in the high resolution models. The frequency change is a bit reduced, but maybe also not that much of a difference. And then for the heavy precipitation, what we have is basically kind of the footprint here of topography, and while in the coarse resolution model, this is not that much visible. Now, having these high resolution simulations, having convection explicitly resolved, what we can also do is then see how these different type of the precipitation is changing. And this is now work here of Stefan Sobolowski, where they separated this this precipitation into convective, orographic, and stratiform, and they found that basically this large decrease in the precipitation comes actually from decrease in the convective and orographic precipitation, and stratiform precipitation doesn't change that much. So these are still mean precipitation changes as annual kind of here. But so we see that this one is kind of decreasing, but if you look then here into intensity, duration, frequency changes, now this is only convective precipitation for the southern Alps. Here the same results also hold for the other two regions. What you can see that this decrease is basically coming from this lower intensity events, while the large or high intensity events are still increasing. So with this kind of high resolution simulations, we can also get a more detailed kind of view what is happening in these simulations. And the last kind of result here in the in the climate projections that I want to show you is about the uncertainty in these simulations. Now, what we have here, it's a bit more, I think, complex plot, but I'll try to explain it, is that basically we can estimate the total and the modal uncertainty from this simulation. And this is done here with it for the 12-kilometer model and the 3-kilometer model, and for different indices here. The mean precipitation, heavy, and the extreme precipitation. So this is mean, heavy, and extreme precipitation. And then you have, here is a model uncertainty, and here is the total uncertainty. And when you compare these two modeling approaches, you can see that this uncertainties are getting much smaller in the higher resolution simulations for both past and future simulations. Now we have many other papers or studies that are currently analyzing these kilometer scale simulations. Some of them are related to the heat waves, then the temperature, heavy precipitation events, also local wind characteristics, and several others. And a lot of them will be published in the special issue in Climate Dynamics, which will kind of contain all these results from the FPS simulations. Now, the next thing that I want to talk about here is about this data availability or data struggle that we have through these different stages of doing this analysis and the simulations in this FPS. So in the phase one, it was kind of active in the fall, winter of 2019, when we were basically kind of finishing some of the simulations and trying to prepare the papers for the IPCC report. Now, the timing, I mean, as I said, we were just finishing the simulations and we're not able to share such a big amount of the simulations in a very short time period. So what we did is that we basically had the authors which were creating the analysis scripts, and they were sending them to the modeler or data provider, and then the modeler or data provider would execute the scripts and prepare the final fields ready for plotting, and he would or she would then share those with the author. And this kind of worked quite okay. I mean, some of the people were not happy because, I mean, they also then spend a lot of time on getting these scripts to run, and it's basically taking the time from their own analysis. And then in the phase two, which was active from 2020 and is still active, is basically that we have data available through Jülich Supercomputing Center. So you need to request the account and permission for from different groups to use the data. And then next year, the data will be uploaded to ESGF nodes. So it's not easy to provide or to share this data as we have done before with typical or standard Cortex or CMIP 5 and CMIP 6 simulations. Okay, so I now come to the summary about climate change projections. So we see that the models with the kilometer scale resolution alter the signal, provide more detailed information and more certain results. Now, what's happening in other regions? Unfortunately, the results are not so further away there. So, for example, here we have these different regions which I mentioned done in the EUCP project. So basically what they did there, they were patching these different regions into kind of the European scale simulations. So different groups were running those different regions. In addition to those, they also did the Caribbean, Madeira and Canary Islands, and La Reunion. And here it's just one kind of illustration how these kind of models are also able to reproduce these tropical cyclones here. So this is the example of Hirma and forecast by Harmony, but there as well they see a large model spread in these simulations. Another example of applying these high-resolution models to different regions is another Cortex FPS, and this is the third poll, where we are basically doing the same as over the Alps, but over the high mountain Asia. And this is the abbreviation of this CPTP project. This is the domain, the minimum domain that we are supposed to simulate, but I mean, it's recommended actually to use this domain too. And the simulation setup of that one is very similar as for Cortex FPS Alps. The maximum grid spacing is around 5 kilometers. And we currently have completed runs for 3 case studies and hydrological year of 2019 and 2020. And here the data is now available through National Tibetan Plateau Data Center and currently also only to the CPTP members. I'll show you also a couple of results from that because it kind of also underlines maybe also the same challenges, but at different degree. So the first results here is the simulations of the mesoscale convective system, which occur in on July 18 in 2008. And here you can see these different simulations done, also different observations. And as you can also see here, basically the same as over the Alps, that this variability between the models is still quite large, but also the observational kind of uncertainty is even larger than what we saw over the Alpine region. We also did some simulations with Cosmo here, which I indicate here, which kind of perform quite okay in comparison to other models. Now we are currently in the process of evaluation of the annual simulations. And here again, we can highlight kind of these differences between different observations. And as I said, I mean, this is kind of getting even larger than over the Alpine region. Now, being in a group that is dealing also with the glaciers, I mean, we were quite happy, the simulation was not perfect. It had some of the biases, but as I said, being like in a group with the glacier, people doing glacier modeling, they kind of wanted to use this simulation to force the glacier models. And then they started to dig into representation of the glaciers in our models, so for example, into the glacier mask. And they started to see some kind of strange things. And the slide, the picture here, what I show you is the kind of comparison of this default Cosmo soil map with this gum dam inventory. And what you can basically see is that in many of these areas we have the overestimated glacier mask, which was not quite nice, considering that we want to utilize this simulation further for our for the glacier simulations. And then what we did basically, we compared it like with another one. We found better results. Actually, we also wanted to implement this gum dam glacier mask, but this didn't work quite well, so we had to kind of settle down for this one, and we are currently kind of in the process of producing the results with this new glacier mask, and then we will see what kind of larger effect this has. I come to the summary. So basically, the transfer of how to knowledge and experience might not be so simple, but worth of doing to gain a deeper understanding of the models in different environments. The challenges I have mentioned through these presentations, and I list them here. These are the observational uncertainty, data storage and sharing, downscaling method, process-based evaluation, which is kind of missing with these simulations, and also the input or external parameter data. And I just have like one slide on worth of mentioning is how to further utilize these kilometer scale climate models and simulations. So currently we are also running this Cosmo model with a hail and lightning diagnostic to project hail and lightning. And here is just some first results, how this hail would change over the Alpine region. And then we also have a project that will start next month, which will compare this kilometer scale simulation data obtained with dynamical and statistical downscaling to see, and the focus will be more on the process-based evaluation to see what we are missing and are we really kind of, is it kind of really worth of spending so many resources on dynamical downscaling when we can, if we can obtain the similar results with the statistical downscaling. And then brings me to the end, and I just want to thank you for your attentions and thank also to all co-authors and collaborators. Thanks. Sorry for running so long.
We have 5 minutes for questions. Kat?
Yeah, thanks, Nicolina. It's really brilliant to see all the pioneering work I think that the various groups have done looking at these kilometer scale simulations with the regional models. I just wondered, as we move to the now global models at these higher resolutions, and they are, you know, the driving data is so much better, should we be rethinking the experimental design, or at least for some aspects? I mean, you've shown how we can deliver new information to users using the kind of downscaling approaches, but there's also the question about, you know, how do we use regional models with the kilometer scale global models to really develop the understanding, and does that demand a rather different approach, larger domains, for example, or something like that? Can we use the two in combination together to really explore the questions of the, you know, how do we improve these models, how do we get to the kind of kilometer scale global simulations that we really want?
Mm-hmm. I mean, definitely. I mean, I guess we should rethink some of the approaches that we are doing. I mean, not only like for these global kind of simulations, but also when we go down, I mean, basically down to the bottom of this downscaling chain. If we are now getting like better simulations, I mean, many of these kind of impact studies or the impact models are also using some correction methods on this data. So this data has like a bunch of large biases, and then you apply some kind of correction, and then you use that further. So I think, I mean, this has to be kind of still compared and see like what do we get right, and do we get right for right reason, and so on, and see how we then can adapt to that. There are different options, of course, but at the moment, I don't know which one of those is the best. Yeah.
So I have a follow-on question from that, which is slightly broader than this. How ready is this community, which is very product-driven and very, let's make high-resolution simulations with as many models as we can over as many regions as we can, right, the Cortex community, to becoming more inquiry-driven, right, which is sort of to help us understand what's wrong with these models and how we could improve them. So for instance, I had a concrete question, and you've probably done it, or maybe you haven't, in your how much of the improvement comes from the better representation of the orography, and how much comes from actually having 3-kilometer resolution? In other words, have you run the 3-kilometer model with the 12-kilometer orography? And how much worse does it get if you do that?
No.
Or doesn't it get worse? So these sorts of experiments, and it brings me to, how ready is your community to run over the ocean? I saw a few tropical cyclone examples there, but you know, to figure out and to help global models to get better at high resolution, we probably want you to run over the ocean.
No.
People will probably be very uninterested because it's sort of just science, and you can't really sell anything to customers as a result. So I'm just wondering, how can we bring this together, the bits of your community that want to do inquiry-based stuff with the global folks who have to make this kind of model work everywhere on Earth, which is kind of hard.
Yeah. Well, I hope I managed to capture all I think there were a bit of different questions, and the first was kind of this related to how much does it come from the convection switching off and how much from higher.
Concrete example.
Yeah, so, and how ready it is. I mean, what I'm trying to also highlight, maybe I didn't manage to do that because I was hurrying like here with the presentation, is that I think we, at some point, we also have to stop just running these simulations because we are racing against ourselves. And there are so many, these simulations which are not, as I said, properly analyzed, so we don't know what's happening like with other variables, what's happening with the processes that are inside. So I think we really have to first focus on this analysis before starting to produce new that kind of simulations. And I think this comparing this alpine domain and Tibetan plateau, it helped us kind of to understand the differences between the regions. And for example, some of the things that worked well over the Alps are not working anymore over another region. And I think this is where the problem also kind of rises. So for example, this glacier mask, there are some glaciers in the Alps, but maybe not that many. And now when you go to the different region where this is kind of more pronounced, you start to kind of wonder like how well this glacier mask is represented in this model. And there are so many, I think, other things inside that we still are probably not aware of. And I was not aware of when I started to do these simulations over the Alps of this glacier mask. I was totally oblivious to that. It's not because, I don't know, some reason, but I came kind of to into the community, which was kind of doing this stuff. And then kind of they bring the awareness to that. So I think, also this collaboration and communication across our community will be important as well to recognize as many of these kind of potential issues.
Thank you, Nicolina. We have to move on, sorry.
No problem.
So let's find Nicolina later on or continue the discussion in the breakout sessions. Our next invited speaker is Daisuke Takasuka from Jamstack, and he will talk about high-resolution atmospheric simulations with the NICAM model.
This is a difference, right?
That's not yours, isn't it?
Yeah, it's not mine. Okay, thank you. I'm Daisuke Takasuka from Japan Agency for Marine Earth Science and Technology, and thank you for this opportunity. And unfortunately, Chihiro Kodama cannot attend this workshop due to his private reasons. So on behalf of Chihiro, I'd like to talk about the recent progress and challenges of the NICAM climate, K-scale climate modeling as a person doing the actual work. And the presented results are based on the many inputs from the many collaborators as shown in this slides. Yeah. Yeah. This presentation is based on the input of these many collaborators. Okay, as you know, the NICAM has been used as a global cloud convection resolving model, which treats deep convection and bulk cloud processes are explicitly treated. So in this framework, the dynamics are directly coupled to the cloud-related local thermodynamics, and that is the moisture and the surface input. Moisture and the surface input by surface the moisture and the heat input by surface fluxes results from the in situ wind variations computed by explicit fluid dynamics, and in response to the more buoyant column, and the local circulation is instantly formed, and the moisture and the heat is almost locally redistributed within local. So we can consider that the cloud is a fast response without disturbing slow-scale circulations unnecessarily. Related to this, the GCRMs is expected to be able to represent the heat and moisture transport more accurately, and the spontaneous realization of the hierarchical structure of cloud systems. So, in fact, comparing the OLL snapshots of between the coarse resolution simulation and the K-scale simulations, the K-scale NICAM can simulate the TC-like structure embedded in this Fourier sum MJ convective envelopes. So, in consideration of these merits, NICAM has consistently adopted the GCRM framework. And looking back on the past decade, the NICAM with explicit convection has achieved several important simulations. In the ensemble member resolution plane, there are several achievements of 1,000-member ensemble simulations at the S2S scale in anticipation of disaster prevention. And we have also succeeded in the ocean-coupled ensemble simulations targeted at MJO. In addition to this, the resolution integration period, we have passed several significant milestones, such as the 14-kilometer mesh climate simulations, diamond activities, which will be presented by the Tomoki, and about the kilometer mesh global run. So under this stream, the recent advent of the exascale supercomputer Fugaku enabled us to discuss the leap into the ultra-high resolution world as represented by the K-scale climate LAN or the global LES project. This NICAM LES project will be presented by Professor Masaki Sato in this afternoon. So this talk focuses on the K-scale NICAM climate activities. Okay, so in the history of the NICAM studies, the S2S scale experiments have been aggressively conducted, and we have obtained the knowledge that the GCRM have the ability to represent phenomena with relatively fast timescales, such as the tropical cyclone and the MJO. And the representation of this fast solution is a matter of weather focus, which requires solving a fast response to heat and moisture accurately, such as clouds and precipitation. So this is compatible with the GCRM framework. However, just like the relationship between the construction of sound dynamics and the computation of individual molecular motions, it is non-trivial whether the accumulation of fast responses in GCRMs leads to the accurate climate, because the climate simulation required a reasonable interaction between the radiation and moisture clouds maintained as a result of a populated convection. So this is qualitatively different from the weather-focused model. So we have to consider how GCRMs can be revised to simulate good slow solutions such as climate. Okay, as an example of these revisions, the NICAM community has improved the model to be aimed at the better representation of the mean radiation distributions in the high-loss MIP simulations. Specifically, we have updated the single moment cloud microphysics schemes are updated based on the trim observations, especially for ice condensations. And the cloud scheme and the radiation scheme is accurately coupled with each other. So these improvements can really reduce low OLL bias as shown in this figure. But at the same time, as shown in this plot, other biases become prominent, such as the divertices biases or the wake amplitude of the simulated MJO. So that is the solution characteristic of the high-logarithmic NICAM is totally different from that known for the S2S scale experiments. And yeah, so yeah, these diverse characteristics can arise from the not truly convection resolving problem. As described before, the dynamics in GCRMs is explicitly coupled with column physics. So how moisture is redistributed within a column by faster subgrid scale processes can easily control the strength and the time scales of the explicit mesoscale circulations. So for example, the difference in the contributions from the turbulent mixing is a source of the difference in the extent of cloud organizations. So for strong turbulent mix cases, the very efficient turbulent moisture transport tends to inhibit the individual local circulations, leading to the excessively large cloud organizations. So yeah, such issues based on this physics dynamics coupling probably holds true for the K-scale. Because one reason for this speculation is that the biases at the 3.5 kilometer simulations under the higher-mid configuration is very similar to those at the 14 kilometer mesh, such as the double ITCs-like split over the Central Pacific and the deficient precipitation over the Western North Pacific, even in the boreal summer simulations. So yeah, we have to revise these situations. Yeah, despite some challenges as reviewed so far, we have to tackle a problem of how we can simulate realistic fields across various timescales. As for the modeling scientific tasks, the accuracy of the fast solutions should be recovered to the level of S2S scale experiments. So to do this, focusing on fast and local processes, we carefully control the moisture evolution associated with the individual deep convection by revising the microphysics and the turbulent mixing processes. The other is that the good points in slow solutions for the high-res MIP simulations should be kept. So specifically, we reconsider the representation of ice clouds associated with large circulations. And in addition to this, to know the knowledge of these unclear solutions, we further challenges the ocean-coupled climate simulations. Needless to say, there also exist technical computational tasks which is establishing the more efficient processes of very large output data or the accelerated simulations by the introduction of GPU computing or the half precision and so on. Okay, before going into the details of the NICAM K-scale climate activities, we here introduce the improvement, the work for improving the fast solution at the Diamond 2 experiment, which was done by Tamaki Soematsu at NICAM. Yeah, in her work, the simulation scale of the MJO has been greatly improved at the subseasonal scale experiments by parameter tuning of the cloud microphysics and the surface flux schemes. Comparing the OLR snapshots of the simulated under the Harris MIP simulation and the this MJO new settings, therefore the Harris MIP NICAM tends to produce more tissue-like structure, and this MJO convection envelope seems to be split into two vortices. Meanwhile, the MJO NICAMs can generate more organized MJO cloud systems. So these results suggest that even at the K-scale, the model configuration greatly alters the characteristics of convective organization, and it would be very helpful to compare these configurations for better NICAM climate simulations. So yeah, to get the insights about how we control the fast solutions, we compare the moisture evolution associated with individual deep convection. The x-axis is log time, in which log 0 corresponds to the timing of deep convection triggering, and the y-axis is the pressure height. So in both configurations, the shallow to deep moisture transition is well captured, but the MJO NICAM has some differences from the high-res NICAM configurations. One is that the more moisture tends to be accumulated in the PBL, and vice versa in the free troposphere before convection triggering, indicating that the individual convection is harder to be triggered. The other is that the mid-level moistening by convection is more prominent. So these two characteristics certainly support on the moisture convection radiation feedback a longer and a larger timescale, which is advantageous to the MJO representation. However, as it's consistent with the notion, the MGO settings is not so good at the simulating the TC development in which the local circulation is important. So for this model improvement, we have to, for these two configurations, we have to improve the model toward this direction. Okay, so in other words, in K-scale GCRM framework, we have to find the appropriate partitioning between the local mesoscale and the large-scale circulations consciously. If the individual convection is easily triggered and the tropospheric moisture is relatively first overturned, the local and the tight convection can be balanced by substance due to radiative cooling. So we expect that this regime cannot represent the slow systems. Meanwhile, if individual convection is harder to be triggered and the convective moistening is more prominent, the more larger convective organized system can be preferred. But the overemphasis of these characteristics may unnecessarily bring some biases into the slow solutions. So it would be better to take an intermediate feature between the two regimes. For this goal, we updated the model in terms of the following 2 points. One is the retuning of the falling speeds of rain and snow in the microphysics schemes, which is aimed at the changing in the static stability and associated with convection triggering and moisture redistributions. As shown in this figure, which displays the vertical profile of the static stability difference from the high-res-MIP configurations, the stabilization effect due to evaporative cooling or the aperture stabilization by radiative heating is appropriately optimized. In addition to this, to get a better radiation balance, we introduced the cloud ice falling. The other revision is the implementation of the turbulent mixing, new turbulent mixing effects computed by the Reynolds term. This term supplements the moisture diffusions from the CRM grid scales to the CRM resolvable scales, so contributing to more moisture diffusions around individual convective cores without disturbing the individual convection triggering unnecessarily. Okay, so these improvements are based on the many sensitive experiments at 14-kilometer mesh for 1 year. And we actually find this model improves has succeeded in the reducing long-standing biases in terms of both the mean and weather characteristics. For example, this figure shows the time latitude diagram of precipitation over the Central Pacific between the two settings. For the high-res-MIP settings, the double ITC bias is realized, especially for boreal pole. But this bias is largely mitigated in the new NICAM settings. And we also examine the model performance of the boreal winter MJO representation in these half-meter diagrams of the low levels on the wind. And compared to the high-res-MIP simulations, the new configurations can reproduce eastward MJO propagating systems at the inter-season quartz periodicity. So these results becomes closer to the compatibility of the fast and the slow solutions. And toward the further implementing in the slow solutions, we increase the vertical resolutions from the 38 layers to 78 layers. Because we expect that the vertical resolution refinement can contribute to better representation of aperture-thick ice clouds. In fact, the low OLO biases in the 38 layers is largely mitigated for the 78 layer simulations, as shown in this. And we do not show the results here. The mid-latitude circulation, the representation of the mid-latitude circulation, such as the tropospheric westerly jet, is drastically improved by this vertical resolution refinement. And in another point of view, we also focus on the TC intensity simulated in the experiments. This plot shows the relation between the lifetime maximum 10-meter wind speed and central sea level pressure. And first, for the new settings, the relation for weak TCs is improved in both the 38 and the 78 layer simulation, but especially for 78 layer simulations, as indicated by green dots, the number of TCs with more intensity greatly increases. So the vertical resolution refinement preserved the good points in fast solutions for 38 vertical layers, or makes them better in the 78 layer simulations. Okay, so based on this improvement, we have already studied 10 years, 3.5 kilometer simulations. The simulation is from January 1st, 2011, and the other main settings are as follows. Okay, so yeah, this simulation is conducted with the use of a 2% node on the supercomputer Fugaku, and it takes about 7 to 8 months to complete these simulations. So as shown in this movie, the organized crowd system associated with the MJO is relatively well simulated, and the barochromic instabilities are well reproduced. And also, yeah, moisture transportation from the tropics into the mid-latitude is also well simulated, like the Pineapple Express. Yeah. So from now, we will show the preliminary results in the K-scale NICAM climate simulations. So we first compare the annual mean precipitation for the GPCP observation and the K-scale NICAM. The K-scale NICAM can tend to more strong, more abundant precipitation in the tropical regions, but the annual mean precipitation distributions are relatively well represented in terms of the zonal contrast over the Indo-Pacific regions, which means that the more precipitation over the Western North Pacific than over the Indian Ocean or the ITCZ regions. And there is no double ITCZ structure, and the precipitation from storm tracks is also well represented. And this plot shows the frequency of occurrence for the daily mean precipitation, but the K-scale NICAM is drastically represents the observational characteristics because the weaker precipitation is more realized and the less, more intense precipitation is less realized. And we also find that the representation of weather disturbances becomes much more realistic across wide time scales, such as the MJO, tropical cyclones, and precipitation diurnal cycles. This figure is a Hoffman diagram of OLR in boreal winter, and you can see the simultaneous reproducing eastward propagating system over the Indo-Pacific regions. And this plot is the same as shown before, the SLP wind relationship for the simulated TCs. The 14-kilometer simulations have suffered from the realistic SLP wind simulations because the 14-kilometer simulations cannot reproduce more intense TCs. But the K-scale NICAM can simulate very strong TCs, and this SLP wind relationship is very close to the observation. And picking up one of the super typhoons, we plot the snapshots of the precipitation and the SLP for approaching Taiwan. So you can see the double I-wards structure appears, which is one of the very strong typhoon characteristics. And diurnal precipitation, the representation of the diurnal cycle is drastically improved. For example, over the coastal regions of the Sumatra Island in Indonesia, the offshore and inland propagation of convective system is observed. And these observation characters can be very well captured, including the timing of the triggering of diurnal cycles. That is the precipitation systems can develop this afternoon. And one of precipitation systems propagate inland, and the other propagation systems propagate offshore from the midnight. Yeah, this characteristic is very close to the observation. Okay, in addition to the K-scale climate modeling, NICAM climate modeling, decadal run by NICOCO, which is the NICAM coupled with the ocean model COCO with tripole grid system, is now also ongoing. The NICOCO has shown the good performance for the S2S scale phenomena such as the MJO, and it can also capture the ENSO transition as an initial value problem. But we haven't confirmed how the ENSO is reproduced in the GCRM framework, so we evaluate this unclear solution by conducting this long-term coupled simulation of Fugaku. The resolution of the atmosphere and the ocean is 14 kilometer mesh and a quarter degree, respectively, and the configurations of the HIRASMIP and this revised NICAM settings are compared. All the NICOCO simulations are conducted by Yuki Takano in JAMSEC, and the present results are provided by him. Okay, so to show the present NICOCO performance for the ENSO, we show the time series of the Nino 3.4 index. In both configurations, as indicated by blue and red lines, the 1 to 3 year periodic variations are simulated. And in particular, in the first 2 La Nina events is realistically simulated. And surprisingly, the Nino 3.4 for the new settings is realistically simulated until 2013, but this could just be a coincidence. And the light panel shows the SST anomaly distribution regressed onto the Nino 3.4 and indicate that the spatial pattern-based ST associated with the ENSO is roughly captures the observational characteristics. But there is some differences between the NICOCO simulations and the observations. One is the amplitude is a bit larger, and the other is the amplitude maximum shifts westward. So which means that the warmer SST anomalies elongate to the west more. And these bias characteristics tend to be overemphasized for the new settings, but we don't know the reason, which is left for future work. And we also analyze the simulated atmospheric response to the ENSO variability. Looking at the left panel, which shows the precipitation anomalies regressed onto the Nino 3.4, the modulation of precipitation distributions is reasonably reproduced. And related to this, the upper tropospheric velocity potential anomalies is also consistent with the observations, including the teleconnection-like pattern into the middle latitude across the Japan or Mexico. But the configurations, the comparison of these two configurations is different. For example, the response amplitude to the ENSO is different. Specifically for the new settings is response amplitude is larger. The one possible reason for this is the atmospheric stability difference. In the HIRASMIP settings, the atmospheric static stability is much higher due to the upper tropospheric temperature is high bias. So yeah, but anyway, the GCRMs, the ability for GCRMs, at least NICAM, to reproduce the ENSO is not so bad. Okay, so apart from the scientific and modeling tasks, we would like to introduce a technical improvement toward the ultra-high resolution simulations. One of this example is the improvement of the post-process. This work has been done by Chihiro. And while the NICAM output data are on icosahedral grids, but very few people analyze the icosahedral grid systems, analyze or visualize icosahedral grids. So in most cases, the icosahedral grid system should be horizontally interpolated to the corresponding mesh or coarser latron grids. So in the old algorithms, this post-process is a very significant bottleneck, and this process is not weak scaling at all. So this problem is resolved by parallelizing file output at a cost of many lot of bytes for each layer, or reducing the amount of MPPI communication, and using local SSD disk on Fugaku. Yeah, these improvements, as a result, the simulation year per day for this remapping is drastically increased with weak scaling. This improvement greatly helps us analyze and conduct many sensitivity experiments very efficiently. And now let's talk about our future plan and the remaining challenges. In this fiscal year, we are going to complete a 10-year K-scale NICAM run and a NICOCO at a 14-kilometer mesh. So the preliminary, the preliminary results suggest that these simulations can represent more the realistic features across various timescales. So the next step is the centenarian 3.5-kilometer ocean eddy resolving NICOCO simulations in 5 years. So we expect the historical and future climate run and many targets from the extremes to the decadal variability will be argued in this GCRM framework. But it is also a fact that there still remains several challenges to be tackled. One is in fact, the K-scale NICAM has a low OSR bias globally, and the associated global mean SSD drift is realized, which is the opposite sense in the icon simulation. And so this problem is rooted in the poor representation of low clouds. So we have to tackle this problem. And the other points are about the physics dimension coupling problem or the model acceleration by GPU computing, which has been partly achieved for dynamical core by Hisashi Yashiro. Okay, in particular, to tackle the few low cloud problems, we planned several approaches, such as the vertical resolution refinement for the selected physics or the use of the improvement microphysics schemes for mixed phase clouds or the double moment cloud schemes. And another solution is the application, maybe the application of the flux collection as a low cloud parameterization, but its validity is non-trivial at all. The plausible choice is using the throughout cumulus of the shallow convection parameterization, but in the GCRM framework we have taken, we have intentionally avoided this choice and will do, because the separation between the explicit and parameters of convection may be physically ambiguous. But we also acknowledge that this is controversial even at the K-scale community, so it may be worthwhile to discuss this topic. And yeah, physics dimension coupling problem can also affect the low cloud formation. The vertical implicit diffusion depends on the model dynamics time steps. So the PBL development is largely regulated by spatial temporal resolutions. As inferred from the results of the single column experiments, the large time steps corresponds to the apparently small turbulent coefficients, which promotes the low cloud formation. So we should carefully know the resolution dependency, especially for turbulent mixing in the use of the vertical implicit turbulent diffusion scheme. Okay, so lastly, we introduced what kinds of scientific targets we can do in the K-scale coupled modeling. As well in the history of the NICAM community, we can discuss the statistical process, understanding and future prediction of tropical origin organized systems such as the extremes, tropical cyclones, and FJO. And also, ultra-high resolution atmosphere oceans enables us to discuss the air-sea interaction in which the fine scale is important. For example, the NICOCO with 1/10th degree ocean can realistically reproduce the position of Crossio, which is advantageous to the studies around the westerly boundary currents. So the local and the interbasin interaction between the atmosphere and these currents is one of the interesting research topics. And we also challenge the detailed process of the ENSO transition associated with the tropical instability waves. Yeah. Okay, let me summarize my talk. NICAM expanding its field from S2S scale to the climate at a K scale, including ocean coupling. And we have improved the model by reconsidering the behavior of cloud microphysics and turbulent mixing processes, which is aimed at controlling the time scale of fast solutions and accuracy of slow solutions. And using the improved NICAM, we are now conducting the 10-year atmosphere-only simulation at 3.5 kilometer mesh and ocean coupled simulation at 14 kilometer mesh. And the preliminary results suggest that both mean characteristics of weather disturbances are realistically reproduced. And the ocean coupled simulation reasonably simulates the ENSO. And at the same time, the technical improvement has also been done, such as the post-process. And our next plan is the centenarian convection eddy resolving simulations. And the main challenge in this plan is a few low cloud problems, the physical dimension coupling in the GCRP framework. Okay, that's all. Thank you for your attention.
Thank you very much. We have 10 minutes for questions.
Thanks for a great talk. On your very final bullet, your century-long eddy resolving simulations, I think earlier you flagged that you have an option B, maybe, for a 10-kilometer grid simulation set, if I understood correctly.
This centimeter and 3.5 kilometer atmos and the 1/10 degree ocean grid is planned.
You say you might be considering a coarser resolution.
Yeah.
So the question really is what are your considerations going to be about that choice, and maybe what evidence do you need to see in the next 5 years to help you make that decision?
Sorry, I cannot catch up with English.
How will you decide whether you stay with the 3.5 or you will decide actually we'll run it at 10-kilometer resolution? So our evidence is for the use of the 3.5 kilometer or 14 kilometer mesh. And this, our results suggest that the 3.5 kilometer simulations are drastically good in many points, such as the diurnal cycle or tropical cyclones. And the tropical cyclones are very important by the atmos-ocean coupling problem. So 3.5 kilometer is our plan. Yeah.
So you mentioned this issue that if you run at 14 or 7 or 3.5 kilometers, convection isn't really resolved, even at 3.5. It gets better, but it's not really resolved. And then shallow clouds, as you mentioned, are really problematic.
Yes.
And so there's this, and you seem to be solving this problem by tuning microphysics and mixing and things like that, whereas other people continue to use convection parameterization, but with smaller and smaller weight, and then, like, the Met Office does that in their forecast model. And to me, it's unclear which one is the better way, because you're building in lots of compensating errors, right? You know it's wrong, and you make other things wrong to compensate for it. So we all have to do that, right? So do you have a way, do you have some recommendation how we can figure this out as a community, what we should be doing? I mean, it's this gray zone issue that we've been debating for years and years. But do you have an idea how we can be a bit more systematic about this rather than go with our gut feeling, right? My gut feeling is we shouldn't do this.
Yeah, this is a very difficult question. As you mentioned, the shallow convection cannot be represented even over the 100-meter simulations. Choice depends on the philosophy, even in every communities. And at least in the NICAM, then the GCRM framework consistently has been adopted. So we do not plan to use the shallow convection scheme. But
we know there's no right or wrong here. There's just choices, right? And then you have to live with what choice you make. But I wonder, it seems to be not investigated very sort of systematically at the moment. It seems it's more each group makes their choice and off they go. I wish we would do this a bit more systematically.
Yeah.
The good part of not using the cumulus parameterization is we can go to finer resolutions and come back. As long as you're using the parameterizations, you're in a different world, so you don't have the convergence. So that's our strategy. Right?
Yes, so you seem to be settled on doing the couple run with 3.5 kilometer in the atmosphere and 10 kilometer in the ocean. And I wanted to ask if there is any motivation for using 10 kilometer in the ocean. I mean, the ocean is cheap, so 10 kilometer and not 1 or 500 meter or 20 kilometer. Why 10?
Why 10? Yeah. One reason for this one reason for this choice of the 10 kilometer is the different from the completely different from the 20 kilometer ocean grids in terms of the representation on the western boundary columns on the this is the this realistic representation is mandatory to do the research topics. This are LC introduction around the western boundary country regions, including the Japan or the North America, which is very important. But we think that the much finer ocean grids is required, but the computational resource is very, very large. So the 10 kilometer is a reasonable choice at this time.
Jimmy.
Yeah, regarding the shallow convection problem, a lot of new PBL schemes now consider shallow convection as part of them because the thermals are those scales, and some of them can lead to cloud fraction parameterizations as a subgrid process. So that's the other direction to approach it from, is as part of the PBL scheme.
And in this PBL scheme, in the NICAM, the partial cloud fraction is not considered at all. So the PBL scheme does not predict the cloud fraction. But one of plausible candidates is the improved PBL schemes in terms of considering the subgrid cloud fractions. And so as you mentioned.
Stochastic subgrid plume populations and things.
Yes.
Marco.
Hi, thanks for the nice talk, and it looks great. I mean, NICAM looks great. I'm wondering, you said NICAM does great in simulating extreme weather events. You just showed some pretty hand-wavy arguments and plots there. Do you have any quantitative evidence how well NICAM does? For example, precipitation, rainfall intensity distributions, how does it do with equatorial waves? You showed the tropical cyclone pressure-wind relationship, but looking at more than just that, do you have some, can you back your words up?
Yeah, that's an important point. So we have to evaluate the precipitation characteristic in terms of many metrics. We haven't checked the frequency of the extreme events or the distributions, so we plan to analyze this. It is needed to analyze that.
Can I ask a second question, Andreas? Did you check for any skill on, let's say, MJO or tropical cyclones on maybe week-long scales? Can you essentially run your model as a forecast model, and can it pick up MJOs 3 weeks in advance, 4 weeks in advance? So getting into S2S timescales, is there actual predictive skill?
So under this new revised NICAM, I do not show the results by the S2S scale experience, but even at the S2S scale experience, the boreal summer emission convection is very realistically reproduced at 14 kilometers. So we expect that better prediction scale of the emission convection is expected, but sorry, we didn't compute the prediction scale. So yeah,
All right, thanks a lot.
Yeah, thank you for your suggestion.
Time for one more question.
Just because you piqued our interest in talking about this 10-kilometer scale, so we have a new project in Europe called ERA, where we plan to run a couple 10-10 for hundreds of years. So one of the things we spent a year and a half debating is how we spin up such oceans. Do you have a strategy for that, or do you not care? Yes. Do you have any strategy?
Yeah, honestly speaking, we do not have the detailed procedure for the spin up for high resolution. Yeah, but our ocean spin up at present is from the starting point of climatology, ocean climatology, and forced by the atmospheric reanalysis for the 100 years. So the exascale supercomputer, the use of exascale computer makes it possible to spin up the long-term simulation even at the high resolution. So the same strategy will be applicable even at the higher ocean atmos coupled models. Yeah, but this is just a speculation. So yeah, we have to consider that.
Thank you.
Okay, let's thank all the speakers from the morning session again. Thank you. So we're going into lunch now, but before we break for lunch, lunch will be served outside where we had the coffee break. Please, I wanted to remind everybody from the North Bay to bring your things over because we will seal off the North Bay for the breakout sessions later on. I also wanted to remind all the breakout session chairs to meet us over lunch, like Christian, Kat, and Andrew and I, to discuss the breakout sessions. And we will reconvene at 1:30 in here. And,
we also need a little bit of help with the tables. And then as far as eating, you can eat in here. There's an upstairs in the cafeteria, and you can also welcome to eat outside. All those are options. Sun came back out. That's great. EGU 15-minute time block, so that means 12 minutes approximately. So I'll give you a warning at about 2 or 3 minutes to go as I'm chairing the session. So I'll give you a 2-minute warning, so speakers look for me waving my hands. And then we'll have questions after each one. Try to keep it on time, and then there'll be a breakout session and then more contributed talks before the end. So without further ado, Benoit Vanier is the first talk.
Hi, I will give you today an overview of ECMWF activities to develop a digital twin of the Earth as part of the Destination Earth project, which is funded by the European Commission. And I give this presentation on behalf of a very large team, and in particular, Irina Sandu, our science lead, who could not come this week. So in the first phase of the project, which extends to 2024, ECMWF will deliver 2 prototypes of digital twins and the infrastructure around it. The first one is the weather-induced and geophysical extremes digital twin, which is the focus of this presentation. And it will monitor and forecast extreme weather events at a timescale of 5 to 10 days. It is made of a continuous component, which is global and initialized daily, and it will be developed by ECMWF, and an on-demand component, which has a limited domain over Europe, and which will monitor specific events. And this component will be led by Météo France. And then there is the climate adaptation twin, which will be procured, and it will simulate the future climate and provide information at scales which matter to the society and sectors just like the renewable energy sector. So Destination Earth, in the first phase, relies on 2 previous projects, NextGem, which will couple a global convection permitting atmosphere to an eddy resolving ocean. And the idea is to see what is the impact of the small scale on the large scale climate. In the highest configuration, it will couple IFS at a resolution of 3 km with a FESM at a resolution of 4 km. And in the last phase of the project, it will deliver a 30-year coupled simulation. And then there is InSight, which was motivated by the fact that ECMWF still rely on the hydrostatic dynamical core in its operational forecast. So we wanted to see what was the impact of having a non-hydrostatic dynamical core and what was the impact of resolved convection on the representation of tropical cyclones. And the highest resolution that we will use is at 1.5 kilometer in the atmosphere. We have looked at 4 case studies of tropical cyclones with 7-day forecasts. And in the first phase of Destination Earth, the idea is to explore many more types of extreme events. We will explore resolution in IFS up to 4.5 kilometer, and maybe before the end of the first phase, we would like also to test 1.5 kilometer. And we couple the IFS to Orca a quarter of a degree. We will test those extreme events with a catalog of extremes that I will present, and and 2 seasons of continuous forecast, which are quite useful to compute scores. So to give you an idea of the granularity of the phenomenon that we can represent at those scales, I have a video of wind gust in IFS at 4.5 kilometer. And the recent derecho event in Corsica reminds us how those wind gusts are really related to representing correctly the convective scale. And on the right, you see a video of sea ice cover in the Arctic simulated by FESM at 4 kilometer resolution. And you see nicely that this resolution enables the representation of sea ice leads and cracks, which are really important to represent correctly the dynamics of sea ice, but also air-sea interactions, which we know matter for weather forecasting in Europe. So those three projects, they really benefit each other in a seamless way. And I will illustrate that with the result of the first hackathon of NextGem, which identified a very large imbalance in the water budget of IFS, which was degraded at high resolution and when deep convection was switched off. And although we knew that the semi-Lagrangian scheme was non-conserving by nature, there was the idea that it did not really matter for weather forecasts at such a short time range. So a tracer mass fixer was activated for all moist species, and it was found that that corrected the water budget. But it has also a beneficial impact on the energy budget, reducing the TOA imbalance from 6 watts per square meter to less than 1 watt per square meter. And what is interesting is that not only it benefits, the closure of the water budget benefits long-term simulations, but it has also a positive impact on the ECMWF medium range forecast as illustrated in this scorecard. And you see that it's mostly blue, so improved, and in particular, a temperature in the tropics, which I have circled here. So this mass fixer will make its way to the next operational cycle. We have, in NextGem and InSight, investigated the role of resolved convection at all scales. On the left image, Tobias Becker has computed the PDF of precipitation in various IFS setups, and in particular in purple in the operational forecast. And you see that the operational forecast underestimates the heaviest hourly precipitation compared to iMerge in black. But if we switch off the parametrization of convection, we see that resolved deep convection is triggered only under very strong low-level convergence and when the atmosphere is already too unstable, so we generate very large precipitation rates. So at this scale, it's still better to keep the parametrization of deep convection on. What is interesting is that at 1.5 kilometer, there is a convergence of the PDF towards the observations with both deep convection on and off. However, in InSight, we found that if we disable the parametrization of deep convection in red, we tend to intensify too much tropical cyclones with very large deepening rates. So it's still better, at least for tropical cyclone, at a resolution of 1.5 kilometer to keep a bit of deep convection active in the model. We have also explored the role of resolution and a non-hydrostatic dynamical core on the representation of TCs in InSight. What we see is that the largest benefit comes from increasing the resolution from 9 to 4.5 kilometer. And beyond that, it's not so clear that there is an improvement of the intensity of tropical cyclone, or at least it depends on cases. We have also explored that 2.9 kilometer, the impact of having a non-hydrostatic atmosphere, and that's the dashed green curve. And again, it is not very clear that there is an improvement compared to hydrostatic dynamical core. We are still working to make the 1.5 kilometer non-hydrostatic stable, and we will explore that in future. In Destination Earth, the idea is to explore many other types of extreme events, and that includes polar lows, cyclogenesis, rainstorms, floods, to name a few. So we will go beyond just evaluating tropical cyclones. And we have, for that, selected 20 case studies of extreme events, and we selected them because the ECMWF operational deterministic forecast had a difficulty to represent those events. So there is the hope that when we go to a 4.5 kilometer resolution, there might be an improvement in the representation of those extremes. And hopefully before, as I said before the end of phase 1, we will test also the impact of a 1.5 kilometer resolution. So one example of those extreme cases is the storm Adrian, which passed over the north of Italy in 2020. And this storm was selected because it had a tendency to overestimate the precipitation totals in the operational forecast, and also it misplaced precipitation over high orography. And here we see that when we go from 9 to 4.5 kilometer, there is a clear change, in particular in the western north part of Italy. Oops. We see, for instance, here that the precipitation is increased along the orography, the coastal orography, and there is a decrease of precipitation in the most western part of the Po Valley, in better agreement with the observations. And it's necessary to get orographic precipitation well placed over the orography if we want to correctly simulate floods. Another case is the Medican Llanos, which we selected because it underestimated, the operational forecast underestimated precipitation over Greece, and also there was a poor predictability in the probabilistic forecast 2 or 3 days ahead before the storm hit Greece. And here, when we compare the surface wind field against ASCAT, we see that there is a clear improvement from 9 kilometer to 4.5 kilometer. And there is an improvement not only in the position of the storm, but also in the intensity of maximum wind. And as an indirect assessment, we compared the significant wave height simulated by the wave model against observation from satellite altimetry. And we find that at 4.5 kilometer, the quantile distribution represented by the blue and orange crosses nicely fall on a line of slope 1, showing that there is a good agreement. So not only it's an indirect verification, but it's also crucial for the coupling because now the calculation of the drag coefficient includes an information about the sea roughness. To conclude, there is still a lot of work ahead of us to develop a digital twin of the Earth with IFS, and not only we will have to evaluate more the representation of processes at the convective scales and moist processes, as I already mentioned, but in Destination Earth, we have also computed scores for a winter season of forecast initialized daily, and what we see is that when we compare the RMSE of 4.5 kilometer against the 9 kilometer run, there is a degradation of the geopotential height in the northern hemisphere, and there is also a degradation of the RMSE of wind at 100 hectopascal. So there are things that we need to investigate more, whether this is due to the parametrization of surface drag or missing non-hydrostatic effects at this scale remains to be investigated. And so I summarize here a few model developments that will be done in Destination Earth. We'll try to test a new initialization procedure for the land and ocean, and hopefully in a few months we'll be able to present results about that. There will be work done on the coupling between the physics and dynamics, land atmosphere, and ocean wave and sea ice, and also we'll develop new numerical methods and try to make the non-hydrostatic dynamical core stable even at high resolution. Like 1.5 kilometer, and try to implement maybe new turbulent schemes, try to bring TK in IFS. Thanks for listening.
You can also come up to the mics if you have questions.
I was curious about your result about the tropical cyclone intensity, that you needed the deep convection scheme on to get the intensity more or less right.
Mm-hmm.
Could the issue be on your surface layer scheme that when you don't have the deep parameterization on, you're getting too strong fluxes? Or do you know why you have such a strong TC when you don't have the deep convection parameterization on?
I think it's a problem of yeah, I'm not entirely sure. I think it's a problem of convection being triggered. I mean, you need very large convergence before triggering convection, and yeah, you generate convection only when the atmosphere is too unstable. I think that might be the issue, and then you generate very high. I don't know exactly. I mean, that needs to be more investigated. Yeah.
Okay, thanks.
Thanks.
Well, first, I thank the organizing committee give me the opportunity to present some very preliminary result from our UFA so-called unified global forecast system. I'd like to thank a few of my colleagues for this work. On a brief outline, I show a little bit about the evolution of NW forecast scale and the model resolution. Introduction to our UFA system. Look at a few cases for precipitation and hurricane intensity in our high-risk UFS coupled experiments. And talk a little bit about the prospects of running 3 kilometer and global forecast and in NOAA. This is for GFS, but it can be applied to any global NWP forecast. So in the past 40 years or so, you can see the 500 millibar alarming correlation increased by about 0.1 per decade, or your useful forecast scales by 1 day per decade. So there's many factors contribute to this improvement: physics, improvement dynamics, data assimilation. And I think one of the major impact is also really the model data assimilation, model resolution. Let me see if I can. So you can see back in 1984, when we started our NCAP global forecast system, it's around 300 kilometer resolution. Up now, it's 13 kilometer. We changed it in 2015, so almost 8 years we have not changed the horizontal resolution. You can see the gradual increase of the model resolution. It's not one-to-one correspondence, but definitely the increase of model resolution has been played a major factor in improving our weather forecast. So right now in NOAA, we are collaborating with the weather and climate science community to develop a fully coupled Earth system modeling capability for both research and operation at different temporal and spatial scales. Right now in our system, we have these components. The semi-pus is the infrastructure. So this is developed in NCAM. We are using this one. As you all know, we are using the FE3 dipole and the so-called common community physics package, MOM6 Ocean. We have the WaveWatch 3 wave model and CSA6 ICE. Also this GoCard global aerosol model. We're also using the same system for the regional so-called CMAC common community air quality model. The NAND is NOAA MP. So our intention is to use the same system, the same code repository for all the applications, including first regional, the rapid refresh forecast system up to 3 days. There's also online what this fully interactive coupled GCMs with the regional model. Also application for the hurricane analysis and forecast system. For the global, we have the, everyone knows the global forecast system and also global ensemble forecast system. Our next version, the seasonal forecast system called SFS instead of CFS. And also using the same infrastructure for the deep interest application. We're currently developing the second version of the deep interest model based on this system, based on FS3. Right now we have a spectral model running for the deep atmosphere. So this is some very early preliminary experiment, the coupled experiment, including only MOM6 and ice without wave. This is one of the physics options we used. It doesn't matter for my presentation, just demonstrate the influence of the resolution. But for full disclosure, this experiment uses rest deep convection and science shallow convection, GFDR microphysics, and NOAA land surface model. For dipole option, we use the so-called HOT6, the divergence damping scheme, and also the model is 127 layer extends to the mesopods 8 kilometers. And just a single case for Hurricane Florence 10-day forecast. So we run 4 experiments. One is to control our current operation model resolution 13 kilometer, and the second one 3 kilometer with both deep and shallow convection parameterization included. The third one only includes shallow and convection parameterization, and the last one without any convection parameterization. So this is like a layout of my pictures. Upper left is the control 13 kilometer, and the lower left with both deep and shallow. Upper right is only with shallow convection, and the lower right without convection parameterization. First, I look at the convective precipitation. So it looks like the scheme is indeed scale well to a certain degree. So you can see, you compare the total precipitation from the convection, the 13 kilometer, and now it's down to 0.5, 0.6 millimeter per day with, if you use a 3 kilometer resolution. This with all the convection included. This only with shallow convection. So you can see the shallow convection in this case contributes very little to the total convective precipitation. The scale well is achieved using our Carver approach. One thing you notice, if you look at the total precipitation, this is global mean, these numbers. They don't change much from from 1 to 1. They're all around 3 and all 3.2 is the maximum. One thing you notice here, for the 13 kilometer, there's not those blue corners. But for the other, the 3 kilometer runs, you have this the blue corner. But the total is almost the same. That means the precip intensity should be increased. You get the same global mean. So to prove this, I made some plots. This is the precipitation, the logarithmic scale, the PDF, from 0.1 millimeter per day to 100. And the vertical is the number of points of count. You can say for this 13 kilometer model, there's a peak around 1 millimeter per day. But for the 3 kilometer, basically flat is reduced, not just reduced. For this, in this 1 meter per day range, so basically from the small scale up to about 3 meters per day. And in this range, around 10 millimeter per day, the 3 kilometer actually increased in the counts. If you look in another way, here I plotted the precipitation and also the column integer precipitate water. That means here in this for the 13 kilometer, you require this PWAT to precip. That means the model is easier to precip, to run out. The circuit is this much difficult. But in this range, once we go to like 3 up to 10, and the 3 kilometer model is easier to run out than the 13 kilometer. With very high swim, it's reversed, but I have to say, because there are very limited samples, there's only a single run. May not be robust, but this is an interesting feature to look into how the precipitation efficiency changed with the model resolution. Then I looked at the distribution of all the hydrometers, the xenomine cross-section. One thing I noticed is there the major difference in liquid cloud water. You can say this one, and this one, they all included the convective parameterization. Only this lower right, without the parameterization of the convection, you can say the liquid cloud water is limited in the boundary layer near the surface. For others, they are almost the same, only looks like the graph and zone stronger in the 3 kilometer runs. But there are not much difference from the 13 kilometer. The major difference comes from this one. So if you look into in more detail to zoom in this, you can see this cloud water really in the boundary layer. So what's the problem? Without any parameterization, the cloud water just limits the boundaries because the PPR scheme is not working right, or it's because the model resolution is really not high enough to resolve convection. You need to go to say 500 meter, 100 meter to really have strong vertical velocity bring the moisture up to above the PPR. All the PPR parameterization is not working anymore. We should reconsider this PPR scheme. I don't have answer there. I'll be quick. So for this one, we also done another, check the hurricane trunk intensity. None of this scheme and these runs capture the ramped intensification, and there are operational models, so we can measure off. But with from the 3 kilometer, with the convection parameterization, same intensity and trunk both are better than the 3 kilometer without a convection scheme. Again, this is a single case. Another thing I found very interesting is the ohm core and the vertical structure of the storm. On the right-hand side is from analysis. You can see 3 kilometer with the deep convection parameterization, it matched the observation or analysis very well, both the intensity and the ohm core structure. But without the 3 kilometer, without the deep convection, really the ohm core doesn't look like the observation, and also much weaker the storm. So this is our current operational computer. It has 2,560 nodes, about 328K cores. Based on what we found from the 3 kilometer operational model and the 3 kilometer run, if we want to meet the 8 minutes per day operational requirement, that means we have to deliver the product to the users within 8 minutes for each forecast day. So we need around 536K cores. That's about double the current our operational capability. So it's still probably a long way to go, and if you want to really go to 3 kilometer global model. So my summary, I guess some of the findings have been mentioned in the morning. But in terms of a computational cost, it probably require twice our current operational model, operational machine, so WCAS2, and require 16 times more disk space. While 3 kilometer without parameterized convection is probably still not working very well, and we have many different physics dynamics probably to work with. In terms of the disk space, we have been using the compressed lattice CDF. It's about 5 times reduction of the original size. I stop there. Take questions.
Can you say a little bit about how the divergence damping in the model affects the convection on the 3-kilometer grid?
We tried that in the regional model, not in this one. In the RFS, we reduced the divergence damping from troposphere down to the surface using the potential profile, and it really improved the 3-kilometer run convection structure and reduced the overly predict radar reflectivity.
Were there any negative side effects?
We haven't seen so far. Only in our phase, we were not looking everything, only like the rainfall. Since the rainfall improved and also the radar reflectivity improved. On this, we haven't checked the other things.
Thank you very much. This one. I talk about the current activity toward the global so-called LES simulation. 2 months ago, we have just presented preparation, but today I can show the result. So previously, about 10 years ago, we have a resolution dependency of NICAM toward the 870 meters from, from 28 kilometer, 14, 7, 3.5, 1.7, 870 meters. The OLR looks similar, but the vertical velocity is changing. We found less than 2 kilometer vertical velocity becomes resolving, but intensity is changing. So we want to see final resolution. So there's a knowledge about the resolution dependency for the deep convective clouds. The Bryan's results show the kind of 100 meters need to have a convergence of the vertical velocity associated deep convection. Convergence in general have much higher resolution for shallow clouds, kind of centimeters scale. But the deep convection kilometer model is a very good property, and the 100 meters scale has a even better, but most is over kilometers. So that's why people are staying around kilometer, but we know 100 meter is as a much better representations, and also this characteristic is known as a NWP forecasting. So we want to go beyond kilometer and go to the 100 meters. So we want to evaluate these results. We are currently running kilometer scale. So the 100-meter model is kind of more reference, but we want to evaluate this model by observation. So we point out the 3 kinds of observation for the vertical winds or motions. So vertical winds or motions are not well resolved, have been not well resolved or observed in both observation and simulations. But currently, many kinds of detailed observation are available. So we want to use these observations. So we just briefly introduce this one. The EarthCare satellite will launch next year. It's still planned. But we should point out this as the first Doppler radar from the space. So this satellite can capture vertical motion of clouds. So currently we have a ground observation for in Japan, Tokyo area. So this observes Doppler velocity, vertical Doppler velocity. So we can use this information for validation of NICAM result, this one. So we can see the vertical motion of ice and liquids. So this is actually used to the model improvement or validation. The second one is the atmospheric radar. This is one in the Arctic area. This is courtesy of Kaoru Sato. So Panji radar capture vertical motion like this one. So WRF model simulation showed about hectare model is very well for this resolution, this observation. And we have in many city areas run radar networks. In Tokyo area, in particular, we have a very variety of observations. So this shows the Doppler velocities radar result. This observation can be compared with the model resolution. So actually, we use this information, the validation of the turbulence scheme. So this kind of detailed observation are useful. So we want to fully use for model improvements or validation. So under this situation, we going toward the higher resolution. Target resolution is 220 meters on the global domain. We call it G level 15. So we have done a lot of activity toward this model resolution. For dynamics, current NICAM cannot be run for the higher resolution. We have changed the grid modification. Physics, we introduced LES scheme and gray zone scheme. So computational aspect, we have done a lot of improvements. So the simulation strategy is we start from 3.5. This is the same as Diamond Summer case, 2016, August, spin-up run for 4 days. We use this run for 1.7 and 817 for the 1 day. And these information we run 440 and 220s. Currently, we just run 2 hours for 220 meters. So it's still kind of a spin-up phase. We want to run at least 8 hours. It's kind of a regional model integration. Okay, this is a result, a global view of 3.5 toward 220 meters. So OLR looks similar, so not so amazing. Animation only show the 450 meters, so I think I can run the animation, but can I run? Which? This one, okay. Okay. Yeah, it's still moving. So maybe this kind of global picture cannot see the power of high resolution. So we need to zoom up. So this is a Pacific domain associated tropical cyclone. So OLR looks similar, but becomes finer. Precipitation, we see the difference. 3.5 kilometer have a very big blob, and for kind of this resolution, we have very contrast, weak and strong precipitation. So this may be familiar for regional model people, but it looks, we know, we can see this resolution from the 817 kind of characteristic becomes changes. So the better represent deep convection, 100 meters simulation has a good result. Okay, vertical velocity. Well, this is 3.5 kilometer larger domain. Vertical velocity field averaging 1.1 degree, it looks like this difference. So we can see kind of systematic change. So this is a native grid vertical velocity, different levels and different resolution. So this shows the general idea for vertical velocities representation. In the middle of troposphere, we can see vertical velocity upper motion becomes stronger, and this area becomes kind of more. Okay, this is a kind of preliminary analysis of statistics. We have a 2.5 degree box and calculate maximum of vertical wind. So this shows the maximum vertical wind of 2.5 degree. So this 3.5 resolution, 1.7, 807, 440 meters. Maximum vertical velocity is generally increasing. This is a comparison for two resolution, 1.7, 407 meters, and different levels. I showed this in the previous slide. In the very lower layers, Saharan areas show the vertical motions, but maximum vertical winds is very much because it's a very deep boundary layer. So this is represent this resolution. And also in the upper layer, we have a stronger vertical velocity. Updraft fraction, I think we have never observed this one. So this is the first picture we can see. The upper fraction is kind of 2% in this area. The color scale is very bad, but we can see slightly this area. Maybe we can see transition in the deep to shallow. This is a vertical profile maximum winds. For the solid is median, dashed is 90 percentile. So this is increasing as a resolution, but becoming the sign of conversion in this 440 resolution. This is downward velocities, upward, downward velocity. Fraction. Fraction is more converging in this resolution. In the shallow layer, this is a large fraction. In the upper layer, we have a kind of percent, less than 1%. Okay, this we want to summarize. We have we want to analyze vertical winds or motions. These are unknown from observation simulations. And improvement physics rely on vertical velocity representation, microphysics and boundary layers. So evaluation improvement vertical winds and the physical process by using detailed observation data. We are looking for the Earth-Care satellite and the atmosphere radar like PANSI and the ground observation network called the ULTIMATE. We started global large eddy simulation for 220 meter by NICAM. So first global view of upper motion, upper fraction, and maximum vertical velocities we can present it. So there are a lot of area for analysis. We are listed as here, but I want to stop here. Thank you very much.
Thank you, great talk. Just thinking back on the two previous talks, all these three modeling systems have very different numerics as well. I know we talk a lot about the physics and the grid spacing, but should we also be more concerned about what numerical schemes we use and how diffusive they are? Because this will probably depend or cause a lot of differences at the specific grid spacing, how things like updrafts look.
You're talking about the model dependency?
No, yeah, the numerics in the model. Like there are very different numerics in the IFS model compared to NICAM, for example.
Yeah.
Should we more be concerned about the numerics as well? Because we talk a lot about the grid spacing and the physics so far.
Yeah. Yeah, intercomparison can answer the question. So yeah, details, yeah, kind of representative effective resolution depends on models. So this representative deep convection depends on models. So, but in qualitatively similar results, we for global LES, we are much more concerned with PBL scheme, turbulence scheme. So we tested Smagorinsky scheme like an icon. So we have a better representation of class. So such a qualitative characteristic is similar across the model, I think.
I had a question. So the results you were showing, the 14 corresponded, was that 440? And were the results at 220 meters? Was that the finest that you showed? Like on the last plot? Because some of them only went to 14 and some went to 15.
Currently we have not analyzed the 220 meter. I only did 2 hours, so we need more hours. So we are waiting for the resolution. So we want to analyze 220 meter in the final.
And can you say anything about any computational? I mean, there's obviously computational issues. Can you give a highlight about what one of the biggest challenges has been, maybe?
Yeah, we can using Fugaku. We can run 220 meters safely in the allocated completion time, but the system is not so strong for very high I/O systems. So we are tackling the computer system for running this resolution. But the weak scaling is very good. So ideally, we can run safely on this allocated time space.
Thank you for a very nice talk. Here you mentioned mixed precision version of NICAM. Could you elaborate some more on, like, do you use just single precision and double precision, and which part of your model is?
Yeah, we have a mixed precision, so many parts we introduce single precision, but many room for more. Maybe half precision can be introduced much better. We want to increase vertical resolution. Currently, memory limitation, we cannot have a 1-to-1 aspect ratio. Ideally, we want a 1-to-1 aspect to do. I need a memory saving.
Could you comment on which part of the model you do need double precision, high precision in the?
Yeah, actually, the important thing is saturation calculation. So we used to be a single precision, but it's something strange. We need a double precision for saturation calculation.
Okay, thank you.
Okay, thank you. Yep. Christian's going to give a little bit of an introduction to the breakout sessions, and then we'll have a breakout and coffee, and we'll come back for more talks at the end of the day.
Sato-san.
Yeah, somebody's iPhone.
Okay. Oh, how many cores does this phone have? Who knows? All right, breakout sessions. So I said this morning, and people were laughing, but this workshop can be quite a historical workshop because it's meant to set the scene of how we work together internationally in this area of kilometer scale climate modeling, right? So, you know, there's some documents you can look back in the 90s that set up programs like the GVEX Cloud System Study, which has been hugely successful in helping people parameterize clouds and climate models, land surface, and so on and so forth. So what we are hoping is that this workshop has acts as a similar ignition charge, but we need your help for that to be realized, actually. And so these breakout discussions are probably equally important, if not even more important, than the presentations that we have for you at this workshop. And that's because the field's still relatively young, and it's drawing a lot of attention, right? So the fact that the WCRP even has a lighthouse activity is a sort of sign that it's taken very seriously and it's drawing attention. So the goal of this workshop is to try and set a bit of an agenda for the next few years as to how we work together to make this happen. And as I said, we really need your input to do that. And the breakout groups really are where you get to say what you think should happen in this area over the next 3-5 years, or even over the next decade. So it's really quite important that all of you take this seriously and actually really contribute to the discussions, because we need lots and lots of input from lots and lots of different perspectives. Perspectives across the spheres, perspective across the approaches, perspectives across what scientific challenges do we face, what organizational challenges do we face, what technical challenges do we face, how do we address them. So what we've done is and the other very practical thing for us is we would like to produce a little document at the end of this workshop. Some people call it a white paper. I still don't understand the white, pink, and green paper differences, but they all exist in parliaments and Congress and so on and so forth. It doesn't matter what color the paper is, really. It just matters that it says something substantial. So to do this, we've set up breakout group discussions. There will be discussions every day, starting in about 5 minutes. There's 3 groups. Everybody should be assigned to a group. If you're not, don't panic, just pick one. So if you can't find your name on any of the sign-up sheets, that doesn't matter all that much. You just pick a group and go to it. All right, so there are 3 groups and 4 days worth of sessions, starting today all the way through Thursday, and you will be in the same group every day. So this is a bit different from what you might be used to, but the idea is here that you really can do a deep dive rather than just a shallow sort of discussion and then tomorrow another shallow discussion. We really want you to go deep in your discussions and have the opportunity to come back to issues that you couldn't resolve on a day, but then you had a few beers with friends in the evening and suddenly the solution has occurred to you at 2 o'clock in the morning when you were jet-lagged and you woke up. We want you to bring that back the next day and tell everybody what it is you were thinking at 2 o'clock in the morning. I want to thank the 6 people who have volunteered, or they actually have been volunteered, but now they have volunteered to be moderators for the discussions. So that's Nicolina, you, Fanglin, Rosima, Pierluigi, and Tomoki. Thank you very much for doing that. They are meant to sort of try and herd the cats, and I don't envy their jobs there, but hey, it's not my problem. We have proposed, and I have sent it to all of the people who have formally registered for this workshop, so you should all have a copy. We've proposed a set of questions for you to discuss. The way I look at them is, please do not ignore them, but also feel free to develop new questions, because it's entirely possible, and I'd be very surprised if it wasn't true, that we haven't thought of something that you think is really important to discuss. So take them more as guidance than as it's not an exam, someone said today, right? You're not passing an exam by answering these questions. They are really just there to guide your discussions. At the same time, we really need some input on them because it will help us set up a few activities. There's an online Google document for each of the groups. It's printed outside there, but really that's useless, right? Who wants to type a link of 200 characters? So again, what I sent you yesterday has that in for your group. And we want you to write comments in that Google document. You can do that as part of your discussion every day, or you can do it at 2 o'clock in the morning when you can't sleep anymore because you're jet-lagged. Just get up and type a few more comments. Why not? So what I'm saying is these Google documents are open all week. Whenever you feel you want to make a comment, do so. If you're comfortable, please identify yourself, and it's really good to put your name there in front of your comment, because you can be, otherwise you'll be the anonymous rabbit or the anonymous whatever. Please put your names there, because Google Doc doesn't always get it right in identifying you. Depends whether you're signed into Google or not and all that. So please put your name there if you're comfortable, but if you're not, keep it anonymous. If you put your name there, we may come back to you to clarify what you meant with something you wrote at 2 o'clock in the morning. And then to help the whole process, we have a short plenary session tomorrow after your breakout session. We won't today, we don't have time. And also on Wednesday, where we come together for half an hour just to see how things are going, compare notes, and see how people feel. On Friday, each of the groups has to report back, and then we have a final plenary session. And again, this session will be more successful if there are more people in the room. Otherwise, our views will dominate. The views of a small number of people will dominate, and that's not exactly what we would like to achieve here. Okay. The only other thing to say, the questions cover sort of 3 areas. There may be other areas you discover in your discussions that you want to add. So there's a bunch of questions around the science challenges of this. and we've seen a few today. There's a few questions around the technical challenges, and we've seen a few today of those as well. But because we are a WCRP workshop, we've also thrown in a few questions around organizational challenges, as in how might we organize ourselves as a community, what sort of activities should we undertake. So we would like you to think about all three. And that's it, really. Now, I have brought up the document to just tell everybody where they go. So breakout group 1, which is the group, I won't even try to name people in this group, but Hugh and Rosima will moderate that. You are upstairs, second floor, in front, windows facing lobby. Yes, if the people from NCAR in this group, who are in group 1, if you could heard your colleagues up there, that would be very helpful. Oh, okay. All right, so group 2, which is led by Nicolina and Fang Lin, you are here, South Bay, that's us, right? That's this room, so you're staying here. And then group 3, Pierluigi and Tomoki as moderators, you are going just next door.
Well, hope the breakout discussions went well. Now everybody's fortified with a little caffeine and sugar. Hopefully stay awake for the last hour and a half. So we have 6 contributed talks, and then following this session, we will also, there'll be an icebreaker reception with food and drinks in the lobby. So that means we're going to try to stay on time, because we don't want to postpone that any more than we have to. And so without further ado, we'll start with Hugh Lewis. And again, I'm going to give everybody a 2-minute, I'll be waving my hands for a 2-minute warning at about 10 minutes that indicates you're getting to the end of your sort of 12-minute time, so we have time for questions. Go ahead.
Slides appear. Here we go. So yeah, welcome back everybody. It's a real privilege to talk to you and to be part of this meeting. I'm going to give us an introduction to what I'm calling the K-Scale UK project and hopefully give some perspectives that will help us through this week. I'm going to test the chair's patience by providing far too much material for the time available, but with some purpose, hopefully to just show you, open a few boxes that we can then talk about in a lot more detail through the week. So I'll go relatively quickly and hope everyone's okay to keep up a bit. In terms of an overview for this K-Scale project, really to focus maybe on this middle box about what we're up to. So in common with a number of groups, we're developing and evaluating kilometre grid scale simulations on large regional and global domains. But I guess one narrative that hasn't really come out today so far is our scientific rationale for doing that. And this may come clearer by the end of the talk. But in terms of what we're missing currently, the hypothesis behind what we're doing is trying to assess the extent to which by resolving convection on large grid scales or global models, we're able to represent the upscale of that convective information onto the larger scales and therefore have a fundamental impact on the large scale climate. And that's really our number one priority for, or the hypothesis we're trying to assess in this whole project. So you might actually find mid-talk I'll change this K-scale title to upscale, because I think that's probably a better description of what we're really interested in. It's a flagship project within the Met Office, and as I'll try and emphasize to you, it cuts across global to regional and weather to climate dimensions. It's absolutely essential for this project to work that we align with international efforts, and that's why this week is so important. Therefore, really very keen to collaborate with as many of you who are interested in the room, and please get in touch directly to learn more. I thought I'd try and work through 4 what I'm calling foundational elements, things I've been thinking about as we develop this project. And essentially they boil down to experimental designs, our use of parameterizations, how we balance the short-term versus the long-term simulations to get to where we're wanting to go, and some comments about ensuring that we stay rooted in what's, I know, key to a lot of our motivations is being rooted in this weather to climate service mission. So hopefully these will make a bit more sense by the end. To start with this traceable experimental framework, these are illustrations of our laboratory. So this is a unified model. We've got a global 5-kilometre setup that you can see illustrated here. And then within that, or aside that, we've essentially made our regional models bigger to the extent that on the bottom here you can see what we're calling a cyclic tropical channel. So we've knocked out the east-west boundaries. And the motivation here is that we can use that, we trust, as a more efficient laboratory to explore these upscale influences. We're maintaining the tropical waves, but hopefully being able to explore some of these processes in a more efficient manner than running globally. And then the illustration here is of Southeast Asia, where maybe our more traditional continental to national scale limited area models are also part of that framework. Along the bottom, I'm just highlighting that we've got 3 kind of timescales to think about. So there's the annual to multi-annual scales to understand and assess model climatologies. In the middle is kind of, if you like, the season length ensemble experiments to explore well, really to get to the heart of that upscale process, so teleconnections, but of the sort of seasonal length. And then absolutely not forgetting the shorter hours to weeks time slot for hazard events, and really using that mix of domains, scales, and timescales to explore this question. Just as a first sort of headline of what our results are looking like, on the left-hand side here, I'm just comparing a 5-kilometre global simulation with then a same grid, but on this tropical channel, and then a higher resolution tropical channel. The headline here is essentially they're looking kind of reassuringly similar, Although if you're an advocate for we must get to 2 kilometres, 1 kilometres or bust, there's perhaps some pause for thought here in terms of it's really very hard to discern the value of that resolution change for these kind of metrics. Maybe a more interesting plot is if we have a look at some outgoing long wave radiation. So let's go cloud spotting. If we had longer, we'd start to take a vote of which of these images you like. This is a zoom in of Southeast Asia. Hopefully you can make out north coast of Australia at the bottom of the plot. And they look kind of similar. They look kind of different in various places. Again, happy to pore over these pictures at some point. Essentially, though, and again, at the heart of all this activity is trying to better represent or understand the influence of better representing convection on the larger scales. To skip ahead, the top 2 rows happen to come from 5-kilometre grids. On the top left, we've got a zoom in of the global simulation. Top right, that's the this tropical channel capability. They look remarkably similar in terms of their structures. And on the bottom row, we've kind of stepped up from 5 kilometres to 2-kilometre resolutions. Bottom right happens to be a circular channel configuration. Bottom left is this limited area model. And away from the boundaries in particular, it's really very hard to see the difference between the limited area model and that channel. So to sort of first insights, first evidence, we've yet to really be able to discriminate that upscale process is having an impact on the larger scale on the right-hand side. Just to dig a bit more into what that global simulation is actually, how we've run it. It turns out it's a global 5-kilometre grid model running with what we call RAL3. So this is the third generation of our regional atmosphere and land science configuration. So that's all of those panels earlier were explicit convection. But this RAL3 configuration has been developed exclusively for limited area modelling, for operational weather forecasting, for national scale climate simulations. And yet we now can run this as what I'm claiming to be a plausible model of everywhere. So it hangs together when we run it on a global grid at 5 kilometres. This is really significant in the sense that RAL3 moves us on from what we used to hang up, what's still in operations and doing a good job, RAL2M for mid-latitudes and RAL2T for tropics. So up until now, we've been running with different configurations for mid-latitudes and tropics because they kind of behave differently. So with RAL3, we've got some unification across domains, and we can now plausibly run this as a model of everywhere. If we look a bit more detail, on the bottom of this plot of just comparing a 10-day mean rainfall accumulation from this RAL3 simulation with GPM, and hopefully the most striking part of these differences is along the ITCZ, where we've got overly intense rainfall, which if you've been working with kilometre scale models for any time, you won't find a particularly surprising result. So it's too intense. It's a good reminder that getting to convective scale in itself is not a panacea, but we've seen plenty of that already this morning. However, it definitely represents a marked improvement on some other current systems. This RAL3 configuration is a useful basis, though, for doing further parameterization exploration. So on the right-hand side here, I've just given you a flavor for if within this RAL3 configuration, we can play with how the aerosols are prescribed, and there's a really quite alarming sensitivity in terms of we can potentially improve on that ITCZ rainfall. This is just to highlight, I think, that it's not all about the kind of baseline atmospheric parameterization, but we really have to take care now of aerosols composition and a number of other aspects of our configurations. This is all running on that same 5-kilometre global grid. This is gives you an insight into what we call GA, or the latest version of our global atmosphere and land configuration. So the key point here is that relative to the first panel, this is running with the convection parameterization within the system. If you then compare the differences in terms of the biases relative to GPM, there are some improvements, certainly around Pacific ITCZ, where we've got less angry, intense rainfall. But the Atlantic ITCZ, for example, has this clear dipole missing. However, that's not, GAL9 is not the end of the story in terms of ongoing development of our parameterization schemes. And so on the right-hand side here, just giving you an illustration of running with the new convection parameterization in development, which in practice is starting to look a bit more like the regional, sort of the configuration developed for convective scale systems, and some of those biases are improved. Some of them are, notably the ITCZ rainfall is getting more intense again. The idea of showing you all of this was really to show that with a flexible experimental design, we can start to really understand the relative sensitivities to some of these parameterization choices. So item 2 of my list was really being able to explore and use those parameterizations to our advantage. And just back to our cloud schemes, you can see that the difference between explicit convection on the left-hand side and parameterized convection are really considerably considerably larger than any influence of resolution in these simulations. We were encouraged to share our dirty laundry, so it's useful to illustrate here a plot of essentially 0, which is good. This is first time step of me trying to run this cyclic tropical channel within the global model using this RAL3 system, and happily it all seems good for the first time step. Slightly annoyingly, at time step, at the first hour, this is the difference in surface temperatures between the global domain driver and the cyclic channel. I've already got fairly alarming surface temperature differences. It's kind of because I cut some corners and I used one set of ancillaries for one model and another set of ancillaries for another, which is really a useful advert for Martin Best talking tomorrow about land surface, and don't ignore your land surface parameterization. Okay, a quick canter on the balance between short-term and long-term simulations to understand the likely benefits. All I'm doing here is just comparing that 10-day difference in rainfall accumulation now for the GL9 configuration on the top with a 20-year coarse 135-kilometer resolution annual precip. And okay, they're absolutely not identical. You know, they're not the same, but there are some interesting equivalents between those two plots. So again, you can learn an awful lot from running more short duration simulations. Similar story on the regional side of things, so just showing the influence of moving from RAL2 to RAL3 in terms of reducing the intense rainfall, so RAL3 is considerably better. And then the kind of frequency distribution plot there is showing you the illustration of testing in lambs over a month, so there's a lot more data going into those frequency curves, but the headline story is common. That's not to say we're going to do all of our work on 10-day simulations and draw conclusions. So in terms of our climate plans, really the evolution from, say, the CP for Africa capabilities is to address things like the rainfall biases over the ocean. So moving again through the lambs and then out into channel and tropical, channel and global configurations to systems. But really the core here is looking at developing coupled climate configurations. Final slide here then is about, well, what am I banging on about with this research rooted in the Weather and Climate Service mission? And for a lot of us, we play with these axes. There seem to be more axes on, in terms of how we use our finite compute power on ensembles, resolution, complexity, and various other axes. So, you know, a driver is how can we get the best value out of the resources we've got. And typically for sort of weather forecast applications, that means we've tended to run order. Now we're down to 10-kilometer global coupled ensembles to get synoptic scale drivers. Then we run our limited area models, switch off the convection scheme, run on grids of sort of kilometer scale for regional convective scale ensembles, and then use those information to generate our assessments of risk and impacts. And we kind of can roll that sort of narrative out from hours, days, weeks, decades ahead. This kind of brings us to the question, though, about establishing benchmarks for this upscale, K-scale work. How much is our model development for climate services really learning from the experience for weather services? So what I've plotted here is the strategy, the current until beaten strategy for weather services. And so I'd emphasize really the importance of this left-hand side, of those synoptic scale drivers getting to kind of 10-kilometer global models. Pierre-Louis had already advertised the ERI project, and looking at 1010 I think is a really important part of our development. So hopefully I've given you a very quick canter through these 4 foundational elements. There are some conclusions that I've drawn as a result on the right-hand side. Maybe just to finish off, I mean, really it's about being clear on the application challenges and designing and agreeing the benchmarks we're aiming to improve. And I think as a community, if we can do that through the week, then we'll have done well. Thanks.
if you're higher, like if you're high extremes and lower frequency, is actually what I would hope for. I think this looks actually more realistic than what the GPM might be.
Yeah, that's another conversation that I want to unpack in the week. Yes, at the risk of sounding too much like a modeler, yes, take GPM with a bit of caution. Is it really getting the high rainfall right, and so on and so forth, and what does reality really look like? So GPM as the only source of rainfall is a bad approach. Happens to be the only source of rainfall I've shown here. Yeah, agreed.
I really like this concept of trying to figure out what's the shortest simulation I can do to learn what about my model. And so I just want to throw the challenge out for this week to think this through a little bit more, and so that we can do it more systematically across the community, because this notion that we all have to run ages of simulations to learn something is pretty flawed, and we kind of know it from the NWP world, but where are the boundaries for what? You know, is 10 days really enough to know your systematic rainfall error, or do we need 30, or do we need 30 years? Or, you know, I just wanted to use this, your results, as a challenge to think this through more systematically. Yep. What's your experience? Do you really think 10 days is, you can learn a lot about the systematic errors? I mean, not talking...
Well, for brevity, I'll answer a different question that you haven't asked.
Okay, yeah, fine.
The 10 days will not be long enough to really give us a conclusion on this upscale aspect.
Yep.
So, you know, it's all well and good me saying, well, we're not really seeing this upscale feedback because we haven't run for long enough. So you need to get to at least diamond, kind of 40-day season length.
Yep.
Whether you need to do a full year is, I think, for us to really work out between us.
Part of this question related to what I showed earlier. I noticed you also made runs with or without convection parameterization. Did you notice any displacement of the hydrometers in the vertical?
Haven't looked, in all honesty. I guess another, so we can absolutely look, and it would be good to compare results.
Just wondering, it's only our model issue, or it's a common issue with all the models? This from the GFS, we see without the convection parameterization, you have all the cloud water sitting in the PAR, not moving up.
Okay, let's discuss. Thank you.
Excuse me. Hi, everyone. I'm Will Crawford from the NRL team. Talk a little bit today about the Navy Earth System Prediction Capability, or Navy SPC. This is our global coupled model that we use for forecasting hours out to weeks. In particular, I'll talk a little bit about our version 1 system, which is now operational, a little bit about the successes we've seen, some of the products we're producing from that, and then also go into some of the version 2 developments that we're working on right now. And I'll just say this is part of a much larger team than just myself. I'm part of the Marine Meteorology Division in Monterey, but this also includes work from our ocean science partners, remote sensing, and space science divisions as well. So as I said, I'll start with a bit about the version 1 system. So really what we're looking at doing is trying to close this gap in terms of Navy capability of producing forecasts on the order of hours to days, where we might use our mesoscale, global weather and ocean models, or seasons, where we might use climatology or historical analogs. We want to develop Navy capability that closes this gap and produces operational forecasts on the order of weeks to months, purposes of ship routing, force positioning, operational preparedness, any number of things. And so this represents a new capability for the Navy, which then comes with new products, and so I'll highlight a little bit about that as we go along. The ESPC system is built upon current operational systems. We have, for the atmosphere, is the NAVGEN model. The ocean, we have NICAM. Some of you might be familiar with that one. And for sea ice, we have the SICE model. And all of these are coupled via the mediator coupler on an hourly time scale. So you see, arrows going between the different component models. So all those went into developing the Navy ESPC version 1, and we'll expand that to include waves in version 2, and I'll get to that further on in the talk. So a general overview, the version 1 ensemble went operational at FINMOC, which is the Fleet Numerical Meteorology and Oceanography Center. It's our operational partner. So the way that NRL works, if you're not familiar, we do a lot of the operational development or development on the operational model, hand that off to our partners, and they maintain it on a day-to-day basis. We went, again, operational in August 2020, and it fills the gap again between weather and climate and provides for us the first time dynamical forecasts beyond 7 days. And in particular, first time ensemble ocean sea ice forecasts are available to the Navy. And as I said, that gives us the opportunity to produce new cool products. So here we have sea ice products. This includes sea ice thickness, and thickness is on the right there, and left hand is sea ice concentration. So that's for a 30-day forecast there in the middle, and then also new tropical forecasts. So we're looking at, now we produce operationally NJO forecasts, here represented by the RMM indices. And I'll talk about this more and more as we go along, but for the V2 system, now I'm on the bottom part of the slide there, new capabilities and upgrades for FY23, new version of NavGem, we're going to be including 2.1, which includes resolution and physics upgrades, as well as a module for including aerosols. We now have one-way coupling to WaveWatch 3. We're migrating to version 6 of SICE, now including tides in our ocean model, as well as a high-altitude component of our atmospheric model. There it says improvements to ensemble design. We've fallen behind on that a little bit, mostly because of computational constraints, but improvements to ensemble design is something dear to my heart, so that's something that'll probably go into ESPC v2.1. So it's written there, but it unfortunately won't make it into V2. Something unique about the ESPC system is the resolution of the operational forecasts of the ocean and ice. So this is the ensemble forecast run at a 12th degree resolution, and so we're looking to produce high fidelity forecasts not only of the atmosphere but of the ocean and the ice. The Navy wants very high resolution of everything on the planet at all times. So this here, of course, represented by the Gulf Stream and then Arctic sea ice thickness on the right hand side there. As far as V1 ensemble products and uses, here is just to illustrate some of the temperature skill of the forecasting system. It's basically showing the same things between the line diagram and the vertical profiles on the right. But what we see in essence is climatology there in green. If we look at a single control member 0, an unperturbed member, we can beat climatology out to about 11 days. Whereas if we use the full ensemble, the ensemble mean, we can beat climatology. So I should say this is root mean squared error, if you can't read. Root mean squared error of ocean temperature from 8 to 500 meters. And the ensemble mean beats climatology out to 32 days there. And on the right-hand side, you see that broken down into a more granular format. We have mean error in the first column, RMSE, and then mean absolute error, ensemble mean on top, climatology on the bottom. And as you can see, again, out to about just beyond 30 days is really where the skill is illuminated there. And that's the right-hand side is there, verification against unassimilated observation profiles. Another success story here is for looking at integrated ice edge air. We have the Arctic on the top, Antarctic on the bottom, ensemble mean there, and plume shown against persistence and climatology. And the Arctic on top, we see we can beat climatology out to 32 days, and in the Antarctic, we beat climatology out to 40 days. So that was a good success story, which leads to now the ESPC system being used by the National Ice Center on a regular basis to inform some of their missions. So those two figures on the right are what I showed before. That's sea ice thickness and concentration. And now this is a story from the National Ice Center where they used the ESPC forecasts to retrieve moorings that belong to the Office of Naval Research, and they used our operational forecast of the sea ice to inform that mission. So this is something now, these figures on the right are what we're producing on a 45-day forecast of mean and spread of all these various ice parameters. Another success story for ice, you can see I'm actually filling in for a colleague here. You can see he's one of our ice experts. We have a lot of ice expertise here. So this is another cool one. This is where they used IceX is a field campaign. It takes place every 2 years. And here they use the ESPC forecast to determine whether or not the camp that was based there on the ice, and they needed to evacuate based on fracturing and flows and whatnot. So the black there shows the observed path that they followed versus the ensemble plume, as well as the ensemble mean there in red. So you can see that it fairly well tracks what actually occurred in the drift, and so they were able to use that information to decide if they were in danger or not. Now, moving on to our new system. So that's all operational now. That's happening, on a weekly basis. We produce those forecasts. V2 is what we're working on at the moment. So as I said, we've expanded now to include WaveWatch 3. So now that's one-way coupling. So you see there's no green arrow feeding back. That is a hope for future versions of ESPC. At the moment, it's one-way coupling to WaveWatch 3. We also include updates to ensemble and data simulation systems in this version 2 upgrade. As I said before, we have ocean tides now in the ESPC ensemble, as well as surface ocean waves to WaveWatch 3, producing those 45-day forecasts of significant wave height, wave spectra, etc. This is some more tabular view of what's changed. We have version 1 on top, version 2 on bottom. We're going from, starting in that first column, going for 45-day forecast once per week to twice per week. We're increasing the atmospheric resolution considerably, going from T359 L60, which is about 37 kilometers, to T681, 19 kilometers, and going from 60 levels to 143. And I'll get into later about just how high in the atmosphere we're going with that. Tides included in the ocean, size 4, WaveWatch 3, and lastly the module for aerosols in the atmosphere, which is really helping with address some of our biases in the model. Here we are with the high altitude I was just mentioning. So now the green there showing our original version of NavGem, where our sponge layer would begin below 40 kilometers. Now we've expanded to beyond up to 100 kilometers, and then the sponge layer being above that. So as the left-hand figure shows, we're really capturing the entirety of the middle atmosphere, which has been discussed a lot in the literature, has implications for tropospheric weather, but for the Navy, it also provides guidance for assets traveling in the middle atmosphere. Lastly, looking at more ice, looking at land-fast ice. This is a 120-day forecast. So the ESPC V2 system, they've really refined the land-fast ice parameterization. If you looking at the figure, the white lines denote the modeled forecast. Cyan is the observed, and you see good agreement between the modeled versus observed land-fast ice extent. Though for version 3, we're looking to expand the scale of this by including spatially varying parameters. With that, this is just a little bit of an overview of the various things you can access if you're interested more in the ESPC system. We have memorandum reports as well as a peer-reviewed publication that came out in the last few years. We continue to participate in the national ESPC effort as well as the NOAA SubX. That's just a little bit more of what I told you on the right for the Navy ESPC system. And with that, I'll say thanks, and I'll take any questions. I'll leave this up. I can hear you okay.
Okay,
Oh,
one of
maybe
your
not.
slides
It's picking up.
said 41 layers in the ocean. How far does that get you in satisfying the Navy's desire to know all about details of the thermocline?
That's a great question. I don't know. I don't know if they've explored what they're leaving on the table by not expanding that. It's a hybrid coordinate, so they changed from a z-based coordinate to a sigma-based coordinate in the vertical. And so I think there's more concentration toward the surface using the z coordinates. But as far as what they're missing and what they'd like to see in the future, I couldn't say. What's your anticipation? What? Oh, for sure. Yeah, and that's what they're worried about, ducting and long transmissions. And so that's why they focus the layers in the thermocline in areas of extreme interest more so than, say, in the deep ocean.
Thanks for that. I guess I was interested in what work you'd done. So you have 16 ensemble members and your future plans for 16 ensemble members. Do you think that's plenty then? Is that compared to I know it's a high resolution workshop, but it sounds like I might have been tempted with more ensemble members and slightly less resolution personally.
And that's actually a conversation we have on an ongoing basis. What the trade-off is, and well, just what you said, right? So where's that breaking point of time versus resolution versus ensemble members versus forecast per week, right? We're all under different constraints as far as our computational power, what we have access to, how often we can test it. I would lean toward more ensemble members if I could. I'm interested in ensemble spread and on spread skill and probabilistic forecasts. not everyone's of the same opinion. Yeah.
So all morning we saw relatively lower resolution oceans, or somewhere the same, forced by relatively higher resolution atmospheres. Yours is the other way around. Is that a deliberate choice? Is there something we should learn? Is there, or is that just how it historically grew?
That's what I mean. That's like, yeah, that's the part of the Navy mission is like prediction from the ocean floor to the top of the atmosphere, or something of that nature. And so I think being the Navy, you know, they obviously are largely interested in protecting assets in the ocean. We've done some experiments using a lower resolution ocean and how that impacts atmospheric scale, which is pretty cool, actually. We're still figuring out how to publish it. But, you know, we see big impacts on atmospheric scale, not big, but we see changes in the biases by increasing resolution in the ocean. Yep. You know, that's a good thing to see. You know, it proves the point of, like, that's why we have this computational cost, is because it obviously impacts the forecast skill. But how it came to be that way, I couldn't say necessarily. Yeah, especially considering computational costs. Like, the atmosphere is a drop in the bucket compared to what the ocean costs. Is that the message? All right, thank you.
So hi everyone, yes, I'm Nikolai Koldunov from Alfred Wegener Institute, which is shortened to AVI, and I'm gonna show you some of our kind of view on how to do high resolution ocean modeling, coupled and uncoupled. And I will start with presenting you the FESN2 ocean model. So this is what we developed in Alfred Wegener Institute, and that's well, basically just yet another ocean model, but on unstructured grid. And the cool thing about unstructured grid is that you can play around with resolution in different places of the Earth. And in this case, you can see that we increase resolution. Well, I mean, on the screen is not really visible, but we increase resolution along the American coast to represent Gulf Stream well. And you cannot really see it here as well, but there is a very nice resolution in the Gibraltar Strait so that the flow is actually going smoothly. In terms of comparison to other regular grid models, we're doing pretty well. So on the left-hand side, you can see the scaling of FESN, and we scale, well, in this case, we are looking at the 1/10 of a degree equivalent mesh in terms of number of degrees of freedom. And you can see that in the ideal case, we scale linearly, and by ideal case, I mean that there is no output, and if we put put an output into the picture, then we scale not that nicely, at least for this publication that we did. But now the problem of I/O is generally solved, so now the throughput is even better. So 1/10 of a degree resolution we can run on 15,000 cores and about, like, I mean, more than 16 simulated years per day. And on the right-hand side, you can see a table from the Tugino et al. That's the model intercomparison project. We are participating in core intercomparison, which is now called OMIP1 and OMIP2. And I deliberately select here the table where we look the best, so we have the highest score for SSS bias, but in principle we are sometimes better, sometimes worse, but we are sort of usual in terms of not an outlier, let's say, among this ocean models in terms of representing hydrography and circulation of the ocean. So you have unstructured mesh. What you can do with that? You can actually do a lot of cool things, and but there are two main directions. One direction is you do the regional modeling, regional ocean modeling, but without nesting. So all of our setups, and I will try to emphasize this throughout the talk, are actually global. So this is not this whitish area, or it doesn't mean that there is nothing here. It means that it's like about 30 kilometer resolution. right? So you can increase the resolution in some particular area and study processes there, being still global, or you can think of how you actually distribute your degrees of freedom in a way that you computationally effective, but also resolve interesting features, well, to the point where you're happy about that. So this is two things that we can do. And we also can do it in a coupled and standalone mode. So imagine you can just take this setup and put it in the coupled model and just continue to do like coupled simulations after testing the uncoupled ones. So this is, first let's start with the global focus and the standalone simulations. Here is the mesh design that we, well, I mean, it's pretty old one. It's actually the first that is follow this philosophy. But that's the one that we used a lot. That's why I'm showing here. And here the mesh, the resolution is refined according to SSH variability. So the resolution goes from 1/4 degree to 1/10 of a degree equivalent. And the number of wet points is actually corresponds to the number of wet points you have in a regular grid 1/4 degree model. And the first question you ask, of course, is how this model actually compares to, in terms of variability, to other high-resolution models. And the answer is we are not that bad. We're actually quite in line with other models, as that's a result from Eric Chessonier's paper, and he compares several high-resolution models that contributed to OMIP2. And, well, FESM is here and is doing pretty well. So then we actually use this philosophy of mesh design to do coupled simulations. And our coupled model called FESM Ecmwf, so the old coupled model was called IVCM, now it's called IVCM1 because we have another two. And the results are, and we contributed to CMIP6 with this model, and we also, well, contributed to high-risk MIP through the Primavera project. And the results of these projects actually keeps coming, and the two nice ones that were published just recently is from Thomas, who compared the high resolution and low resolution responses of temperature, like, I mean, temperature increase, basically, 2-meter temperature increase in high resolution and low resolution, and he finds that actually in high resolution, you have a much smaller temperature response compared to low resolution. And the reason for this is that you have eddies here. And in our setup, we can actually resolve eddies in this region, and that's why the response is pretty different. And in low resolution, of course, the eddy effect is parameterized, and that's why you don't have like, I mean, it all depends on how you parameterize your eddies. And another one is from Nathan, who it just actually comes up last week, and he analyzed the EKE distribution in future. Again, that's only possible because we reproduce very well, well, relatively well, the variability, the SSH variability, or EKE, in the global ocean, and we can look at how the EKE will look in the future. Let's continue with regional focus. That's a standalone simulation, so it's 4 simulations for 1 kilometer resolution, so that's our flagship simulations right now, so this one. And so we publish, well, I mean, it's 11 million degrees of freedom, surface degrees of freedom, so vertices basically of triangles, and we can do 1 simulated year per day with 7,000 cores on this simulation. So there was a paper published by Kyang Wang a couple of years ago where we analyze eddy kinetic energy in these simulations and compare them to 4 kilometer resolution runs. And now what is happening, we also put some more force and analyze the data from the simulations, and this is some preliminary results from Vasco Müller's work, who start to analyze the number of eddy, cyclonic, anticyclonic eddy radius, so do some eddy statistics on these simulations. And that's pretty cool because, I mean, that's 1 kilometer resolution, talking about the ocean, is something that you actually need in order to resolve eddies, mesoscale eddies. So we don't go to sub-mesoscale here because of the Rossby radius. We have to get 1 kilometer resolution in the Arctic to get the eddies. Another example is that we go in also with regional high resolution. Is this? This is regional 1 kilometer resolution model that we use to participate in the SWOT crossover region intercomparison between different models. And the kind of dirty laundry part here is that if you look at this publication, you will see that we actually don't reproduce well. We reproduce well some of the statistics and of the flow, but not all of them. And that's the lesson learned there is that, like for these regimes, you already have to include tides in your model. So without tides, you will be kind of on the on a better end of the spectrum. It consists of 3 million vertices, do one simulated month per day on 2,000 cores. And the highest resolution that we get, still the same configuration, right? So everything is global. This model is also global, but due to particular interest of Sergei Kirillov, we increased the resolution, this particular small region, to 100 meters, and we actually were able to run global model with 100 meter resolution, which we are pretty happy about. And that will be a follow-up work of the paper that he recently published in Ocean Science. And last but not the least, regional simulations is the Southern Ocean. So we are Polar Institute after all, so we have to cover Arctic and Antarctic research. So this is 3 kilometer resolution setup that we have for Southern Ocean. And here, I hope this movie also will start at some point. We show, maybe not, okay. So we show the very nice distribution of sea ice and with quite a bit of detail, and we are sort of proud of it because it takes some time to make it right. And also pretty energetic ACC, so well, there are also people looking at it. And we also can do this, one simulated per year per day if we want to and if we have resources. And the last one, but it's coming to the coupled one, is the example of Xinyu Li research, where she asked the question how the Arctic Ocean surface will look like in 4 kilometer resolution model in the future. Well, and it will look like in the future, and she tested on 4 kilometer resolution model by forcing it by atmospheric fields from CMIP6 models. And yeah, for those who interested in the Arctic, that's how we might have, what kind of currents we might have in 2100 in the Arctic Ocean. Okay, so I'm coming to the end of my time. So what we have in terms of like global, what we kind of use, how we can use this information that we get in the regional and global simulations to move forward. So right now we have two coupled systems that we are going to use in the next, like, I don't know, 10 years. So it's OpenIFS FESM 2 and IFS FESM 2, which is developed together with ECMWF. So this one, for this one, the highest resolution, highest mesh with the highest resolution will look like this. So 10 kilometer on the south, 4 kilometer on the north. For the digital twin of the Earth, there will be about 4 kilometer south and north, and lower resolution in the tropical area. And this is the overview. Maybe I don't really have too much time to do, but I mean, I'll just go quickly through this, of the projects that support the development in Germany and in Europe of this kind of models, and where we will participate in. So NextGems, of course, that was already advertised. So the idea there is that we are going to run for 30 years the IFS FESM at 4.5 kilometer resolution and the NG5 mesh. And there will be experimental setup also with 2.5 kilometer resolution and up to 2 kilometer resolution ocean. The Warm World is the project, is a national project that mostly aims to develop ICAN model, but we also have part there, and there are plans to run IFS FESM at kilometer scale. ERI is something that Pierluigi will talk much better than myself, but there are like centennial scales simulations with 10 kilometer atmosphere and ocean. The ALIF project that where we'll use OpenIFS FESM at 10 kilometer. So also running for 150 years with that resolution. And that's the last one. So that's some first results from the 2.5 kilometer resolution and NG coupled ones. So you can see some imprint of the high resolution aiding ocean in the atmosphere and this mixed layer depth. So and I will stop here. Atmospheric crowd, right?
I'm not sure if it's a quick question, but what are the main parameters that you had to change in the ocean model when you went to very high resolution?
We are not really, we trying to, well, I mean, two main things. You get rid of the GM parameterization, but you kind of get rid of it about at already 10 kilometer resolution. And you have to adjust viscosities quite a lot. Well, you have to adjust the time step. But apart from that, not really much. Yeah, thanks.
This is also a clicker then. This thing is also clicking, okay. Right. So I'm going to talk a little bit about UK climate model developments, and I'll give you a little bit of a history of where we are with that. Just to say, maybe this is all you want to take away. This is something that Benoit Vanier did out of his diamond simulations. These are pre-ensemble members of 5 kilometers. Just to say, if you follow, for instance, if you follow some of these tropical cyclones, there is already a lot happening in those first 40 days. There's a lot we can learn about the model's quality in terms of physical parameterizations and all that. But there is also already a hint that we do need these ensembles, and I'll pick up on that later. So as I said, we've been developing a sort of fleet of climate models at different resolutions for a very long time. We've been at it for over 15 years. We had developed a quarter degree, so 25 kilometers in the atmosphere, 1/4 degree in the ocean for Primavera, which is the project we concluded a couple of years ago, and this was part also of our high-res MIP effort. And now we've been working on these models on 10-10, so I'll show some 10-kilometer results. And so in the ocean, we start to have a fairly eddy-rich regime. We don't fully resolve the eddies, but I will show you it makes a big difference. And then we participate in Diamond, and Benoit has run some simulations here. And sort of the idea is that having this hierarchy of models that are coupled, models that are atmosphere only, has allowed us to learn a little bit about what happens as we go to those resolutions. So as I said, I'll show you a little bit about the 25-kilometer world, and then a few things out of the early results of these sub-10-kilometer and sub-10-kilometer models. So I'll start here. These were exploiting 1 to 10 petaflop computers across Europe, and through high-res MIP, we were able to use a whole community approach, so the results would be more robust. And I can't show you all the results, but just to say that someone has actually compared various CMIP models through various CMIP generations with the high-res MIP, where we have here the high-resolution versions of 25 kilometers. This is a 100-kilometer resolution version of our models. This is for temperature biases and for precipitation biases. And in both cases, you can see that some historic biases start to go away. There's a really important one here in this part of the ocean for precipitation. And you can see also in the North Atlantic, some important errors are reduced. These, we heard just now about going to 112 degree. These become actually worse. So overall, it was not our intention, but overall, there are some encouraging signs that going to this higher resolution is beneficial. But that was not actually our primary purpose. We were more about the processes and chains of processes than about obsessing with error reduction by doing things like tuning. Just to say, as I said, in this region of the world where it's brown, the bias is reduced, and in this part of the world at 25 kilometers and 1/4 degree, the errors become worse. You need to go to the next resolution for this to improve. Now, this is important. The achievement in the North Atlantic is important. I'll show you here. This is a comparison of the SST errors in the Atlantic. Where it's red, it means actually that the error is reduced. And we've looked at what happens as a response to these SST's improvements in terms of frequency of blocking. And so the error in the frequency of blocking is also reduced. And if you look at a metric of a meridional SST gradient versus blocking frequency or north jet frequency, so this trimodal distribution of jet frequency, if you look at when we have a north jet, and if you look at observations here, every model that we ran as a consequence of having improved SSTs, you go from the round dot to the diamond, every model that we had in the intercomparison is going towards the observations. So we improved the SST error, we also improved the blocking frequency, and we improved basically things that have to do with circulation. And this is really important for European weather. You do want to represent blocking, you do want to represent where the jet is. So this is important for understanding the risk of weather extremes, particularly if you have these long blocking periods. I would also say, and this is trying to provoke you, that this is important to point out the potential for picking out GCMs that have the right circulations and downscaling those and putting a lot of resource on those, and then saying, well, these GCMs cannot really do the circulation. It's not really worthwhile to put a massive RCM ensemble onto those. We can discuss this for the rest of the week. Right, I'm done with the 25-kilometer generation. I'll switch now to the 10-kilometer, 112 degree in the ocean generation. So just to say that there was an important paper by Helen Hewitt and Malcolm Robbins et al. in Nature Climate Change recently. Basically, Malcolm had a paper where he shows, again, metrics of AMOC versus north-to heat transport at typical CMIP resolution. These are the OBS in black, and these are various models that participated in CMIP, and then going to half a degree, going to a quarter degree, so these are high-risk MIP, and now looking at eddy-rich models. So we started to develop these eddy-rich models in Primavera, and you can see that as we move through the resolutions, this metric of circulation strength and north heat transport come very, very close to observations. So the SSTs are happening for the right reasons, at least from the point of view of the overturning circulation. Also, in terms of climate change, if we look at the change in the AMOC in the last few years, and you look at the strength of the circulation, again, the crosses and the pluses separate the high-resolution models from the low-resolution models. And it tells you, if you want to predict the slowing down of the AMOC, you need a stronger overall circulation. And so, again, this is where the high-resolution models are more credible. They do it for the right reasons. And again, this is important. If we go now for climate change applications, this is a paper that was published last year looking at changes in precipitation. And this model here doesn't look like, this is the low resolution, and this is a mix of high-resolution atmosphere and high-resolution ocean. But it's only the 112-degree ocean model that gives us this projection of change of precipitation over Europe, so quite extreme precipitation. If you now look at the area averages, this is what they changed. So this is a 15% change using this eddy-resolving, well, eddy-rich model that is outside the envelope of all the other models. It's something, it's a complete outlier. It's something really quite noteworthy, and we should be quite worried about that because it's a model that does something quite different. It has much smaller biases in the Atlantic, and it gives us really, really extreme precipitation. So we need more of those. So a little bit about hurricanes. We've seen in the last many years that as we go to a quarter degree and beyond, we improve the number of hurricanes. We also improve interannual variability. There are lots of things that improve. What was not good was intensity and the typical pressure-wind relationship, but also intensification was not good. With Diamond, we were able to bring the resolution to where normally the regional models are, and Falco Youth had a paper about this showing how all that improves. So this is quite important. As we talk to the public, and this is now the Hawkins and Sutton plot about where the uncertainty lies. If you're looking at global precipitation uncertainty, sorry, global temperature uncertainty, what's coming from internal variability of the system becomes smaller and smaller as we go into the future. And scenario uncertainty becomes quite large. So it's very important we run all those scenarios and all that. And what could be seen as structural model uncertainty is still there, but as we go forward, these scenario uncertainties dominate. When we go to regional temperatures, then the ratio of those starts to change, and so scenario uncertainty is a bit smaller. Interannual variability or internal variability is still rather important, and model uncertainty goes up, so it becomes harder. For precipitation, it's even harder, but Benoit Vernier did something really interesting. He looked at predicting hurricane frequency. And if you look at the Northern Hemisphere or the North Atlantic, you can see the interannual variability is really important, but so is model uncertainty, and scenario actually starts to go away. So this is, again, a justification, both at the hemispheric level and regional level, if we're studying hurricanes, for improving the models, for using models that have that process well represented. But because of this, it's also telling us that we need really good models, we need very high resolution models. It also tells you we need large ensembles. So this is quite tough, because we have been running 2 free ensemble members as a group. So the Diamond group was rather large. We are running 2 free ensemble members in Erie. We are doing it in the group, but possibly for this, we need really large ensembles. So this optimal point of where the ensemble size should be and where the resolution should be, this is an example of one very specific phenomenon we want to predict. Just to say, I've already hinted at this, but just to say that the distribution of intensity categories improves as we go to 5 kilometers, pressure-wind relationship, but this other bit about how quickly we intensify. I don't know if you saw, we had a typhoon in the last 2 or 3 days. It intensified within 6 hours. This is a really tough problem. We do need to be able to predict the intensification as well as the intensity. The other issue is, okay, so as we go to these scales, what exactly is producing the tropical cyclones? So if we run the model at 100 kilometers, at 10 kilometers, at 1 kilometer, is the development, is the genesis responding to the same drivers? What do we call? So a lot of us have written papers about TCCs. What do we call TCCs? So again, Benoit was looking at this in the Diamond simulations. He was looking at now the propagation of organized convection in the Sahel region. So this is at 100 kilometers. So this is for the Diamond period, 20 kilometers, and then 10 kilometers of parameterized convection, 10 kilometers with just the shallow convection, and then going explicit. And then this is the Diamond run, 5 kilometer with only shallow convection, and this is OBS. And you can see already there is quite obvious evidence of the bad diurnal cycle that comes up because we use convective parameterization. But within that, we do see nice propagation of these organized events, quite intense events. And the question is whether any of these could be TCCs. So yes, he has traced one of those to a hurricane. So to what extent these organized systems may end up causing the genesis of tropical cyclones. We also saw that in this particular configuration where we use explicit convection, we end up with a dead zone as the systems come out of Africa and reach the ocean. So maybe that's not terribly promising in terms of genesis, or at least if we want to look at genesis near the African coast versus looking at just the Gulf region. There is a lot already here that we can learn, and then we have looked at the same problem in the current runs, the runs I'm doing are 35 years long each, and we see basically the same behavior. As we had already learned all this with Diamond. We see very much the same behavior. This is 1 year I picked at random. These are the free ensemble members. Again, you see the propagation, and you still see the contamination by the diurnal cycle. Is the diurnal cycle impeding the development of these systems or interfering with the development of these systems? Again, we have traced some of these to TC genesis. So we've also tracked the TCs, and we have matched some of these events with actual TC genesis. But to what extent the fact that the convective parameterization is poor standing in the way of that? Just my last slide, just to say we're going towards high-res MIP2. We want to research high-res MIP2 as a protocol. We want to try and understand these processes and where the balance is in terms of heterogeneous ensemble, homogeneous ensemble, and simulation length. The idea is to make the simulations much longer. Many will run 100 years each. Our group will run 150 years, and we'll try and compare to the full sim deck. The idea is that as we exercise these eddy-rich models, we'll have a stronger interannual variability inside the ocean. We have better air-sea interactions, and we'll have better processes. And the idea is to then run these for these very long periods and to understand what the whole system does and to understand in particular the teleconnections between different parts of the world as we resolve all these processes both in the atmosphere and the ocean. And we can talk more about this during the week. And yeah, that was my last slide. I'll stop here.
So, I mean, you compare ocean simulation with different resolution, and this was also true in the other talks, but I'm wondering, what about the coupling frequency between the atmosphere and the ocean? Do you know how sensitive are the results to different coupling frequency?
I think other groups have done it. We have decided to go to daily coupling a while ago, and we are sort of staying with that. Perhaps if we were to couple at the time step level, it would make a difference. Again, our model is slow and expensive. There are certain compromises that have been made. Maybe other groups can comment about coupling at the time step level. Yeah.
Good afternoon also from my side. I thought initially this is a poster, and when I heard that I have a talk, I changed the title. So I made it a little bit more high level and a little bit more thought provocative, which is fixing biases for good and the long and difficult and rewarding task to improve kilometer scale climate modeling. And I'll give you an example, just one example from what we are doing at NCAR. So at NCAR, we run regional kilometer scale climate models since almost a decade or maybe even longer. We started in a fairly small domain over Colorado. We used the weather research and forecasting model, of course. And once we got more confident in what we are doing, we expanded to larger and larger regions. And at the moment, we're running 2 flagship simulations. The one on North America is in this domain, which is called CONUS 44. It's 40 years or 42 years at 4 kilometers downscaling ERA 5. And the other one is over South America, which is the biggest domain we ran so far. It's very similar to the North American domain. It's 21 years with the 4-kilometer WRF. What I will talk about today is just one example in the central US, which biases we had and how painful and slow it was to improve them and where we are now. So the central US is a really interesting region. Like most climate models and also weather forecasting models have pretty strong and systematic biases. You see this is from the CAUSES project. This is using CMIP5 simulations. They also used other models in here, higher resolution models and regional models. And what you see typically in the central US during summer is you have a pretty strong warm bias and a dry bias. And there's an updated on, okay, this paper basically, the basic conclusion of the CAUSES project was we don't simulate this very strong convective storms well. And that's why we have these biases. So there's an update on this paper recently. They use CMIP6, and you can immediately see how hard this is to fix those problems. Like, they're still there a few years after. Now they have, I think, a little bit better understanding where they're coming from. They talk about land-atmosphere coupling here. What I also want to highlight is that not only the central US is really badly simulated, it's also the western US. Nobody talks about that. I can talk about this. If you're interested, ask me later on. I have a slide on this, how high resolution models are doing there. But for this talk, I focus on the central US. So why is it so difficult to simulate the central US during summertime? It's dominated by mesoscale convective systems. These are organized convective storms. This is a satellite loop that you can see here. And you can clearly see these are hundreds of kilometers, thousands of kilometers long, interactive convection. They make their own weather, basically, and they spin up almost every day. There's another one spinning up here. They produce more than 50% of the rainfall in the central US. And in the summertime, it's more than 80 in some parts. And they're extremely important also in the global scale, especially in the tropics. So if you don't get MCS as well, or correct in your model, your climate will be completely off. The problem is really this is as far away as you can get from this typical classical example of how convective polarizations are built. So those don't work. So that's why it's so difficult to simulate them. The problem with this all is basically which regime you're in simulating turbulence. So if you look at this, this is the turbulence kinetic energy spectrum, approximately. And we have three general regimes. The one is on the left, which is the large regime, where we use deep convection parameterizations. We have hydrostatic dynamics and so on. Then we're getting into this gray zone, which is often referred to as terra incognita. This is basically where we live in here most of the time, this kilometer scales. And then, of course, if you go further down the rabbit hole, you go to LES scales, and you start to resolve all the turbulence that you need in the model. So just to show you how MCSs look like, this is an idealized WRF simulation. The cloud field, how MCSs generally look like if you are in these different regimes. This is a 12-kilometer simulation, so fairly high resolution. Doesn't matter if you use a deep convection scheme or not. And what you see here is you trigger a single updraft, and this is convected by the main flow. So this is very disappointing. If you study MCSs, you're very disappointed now. If you go to 4 kilometers, there's really a regime shift of how these storms look like. There's really a transition between those two grid spacing. And what the main difference is basically you develop a cold pool here, and it's triggering additional updrafts. And then just look at the cloud shield. Even the propagation is very off, or very different between those two. Going further down to 1 kilometers, you can see now, like we resolve the updrafts much better. The cold pool is better simulated, but generally, the characteristics of the whole system look fairly similar, and this is even true if you go to 250 meters. Like the turbulence is much different here, but the biggest change is really once you go from this mesoscale limit to this explicit resolved convection. And this is not only for WRF, like we know this since the 90s for weather forecasting. This is an example using the unified model over the UK. They had a MCS observed here, which was very well forecasted by a 1.5 kilometer version of their model, and look at the 25 kilometers, a little bit drizzling there. So this is fairly well known that we have these big benefits here. So we were really excited about the central ES and using high resolution, and like we probably solved everything by now. So basically what I did here is I tracked MCSs in observations. So this is the radar observations, and these are MCSs per month. You can see in the central US, you get approximately 1 MCS per day. Like it's very active. The domain was basically, the model domain was basically this one. We forced the model with ERA interim and even used spectral nudging. So we were as close as possible to observations. So when we looked, this was a 13-year-long simulation, so we can look at interannual variability a little bit here. When we looked at where the MCS climatology was very nice, like really happy until June, and then everything collapsed. Like we had a third of the MCSs maybe. And associated with that, as you can guess, we have a warm and dry bias. And the frustrating thing here is really it's getting worse. Like this was better at 12 kilometers or 30 kilometers. Now we had, like this is with spectral nudging, we had 8-9 degrees too warm temperatures in the central US. So of course, like we are the National Center for Atmospheric Research, so we went searching for what is causing this bias. Aerosols, like aerosols must cool down the central US. They do, but it's not the dominant effect. Okay, let's do shallow convection. Yeah, shallow convection, we don't do it well. A little bit cooling, it's not the dominant effect. Boundary layer schemes, yeah, we probably do something mixing wrong. Yeah, not really. Like WRF has many options, so we tested a lot. It took us 4 years to figure out what's happening. It's the groundwater. It's the land surface coupling. If you look at the central US, you think it's a flat area. It's not. We have lots of mesoscale river valleys. And you can see this clearly here in this groundwater table depth diagram, where you see all these green areas, which are fairly shallow groundwater tables where you can evaporate a lot. This is scale sensitive. Like what you see here is how many grid cells in this area have a groundwater table depth of less than 5 meters, which is the active root zone, basically. You can see if you run WRF at 30 kilometers, there's almost none. Like we did these experiments, we had maybe 1 degree cooling. So we didn't think that this is sensitive. Once you go to 4 kilometers, you have lots of these grid cells. So you can much more actively access this water. And like the basic thing that you had to simulate is lateral flow of groundwater. You have a net flow out of high regions into low regions, and then you evaporate a lot. So let's see what this effect is. And it's almost mind-blowing. It's 3-4 degrees Celsius. So when we did this, we removed the bias almost completely. And also, like if you look at the MCS climatology, it looks much, much better. Okay. So a few takeaways. If you haven't listened so far, it's fine. Like, these are the 3 points that I want you to remember. The first one is, do not expect that everything gets well if you go to high resolution. It probably won't, because your model is not really set up to do this high resolution scales. It takes a lot of effort to get this right. You probably miss some key processes. The second one, this coupling strength between spheres is grid spacing dependent. And it really takes a multidisciplinary team. We were really fortunate to have land surface modelers in our team that basically brought this up and made the simulations. If we wouldn't have those, we probably would still live with 5 degrees biases in this region. And then, like we talked about this a lot, there's a serious lack of communication between communities, because I think we don't communicate these results well enough. And on the last point, I just want to do a little bit of advertisement. We are hosting a convection permitting workshop. We did this for the 6th time this year. We were in Argentina a few weeks ago. And this is mostly, I would say, a regional workshop, but we really make an effort to try to involve more communities and also involve specifically the global community. So we had some talks this year as well. Kathy gave a talk last year at the workshop, for example. We have the next workshop in Norway. It will be at the end of August next year. So if you're interested, mark your calendars. We have an email address up there where we advertise the workshop. We try to do this as broadly as possible. Write me if you want to sign up. And with that, I just want to leave you with a few nice images of clouds in the South American simulations that we are doing. I think they don't let me show this again. Oh, yeah. Thank you very much.
Are you on? All right. However, it's interesting to me. I'd like you to say a little bit more about the interdisciplinarity, because it still looks like the groundwater was the last thing you looked at, and yet you had surface modelers, but did you have hydrologists who really include those factors? In other words, was the interdisciplinarity of your team sufficient, and how could it have been otherwise organized such that you would have gotten to the solution, maybe not first, but maybe second or third?
I think it's probably not sufficient. I agree. I think the thing that held us back was we did these experiments with 30 kilometers, and there was very little sensitivity. So we were basically surprised to see this high sensitivity at high resolution. I think this was the main issue, that we didn't test this earlier. We have hydrology, like you know, Uniral, like we have hydrologists, and even if you're in one institute, it's sometimes very hard to collaborate. So it's not only a problem in the larger research community, it can be even in your own research community where you have this coordination problems.
I have two. I don't know which one to start with. I'll start with the science one. So given that this is so resolution sensitive, and given that we're still going to run, despite this being the high resolution crowd, we're still going to run 10 kilometers or worse, or coarser, for a long, long time, what do we do over North America to get rid of this error, which every GCM has?
Like this region that we're looking at had the same issue, the Plata Basin, very similar with the groundwater. There are efforts to have subgrid scale orography included in the surface models and to get these flows correct. Like this is another way to go, but you really have to resolve the slopes, otherwise you won't get the effect.
And then my second question is, what do we do to not overload the community with workshops? So you have your long-standing workshops, so do other fields. Now we have Digital Earth, La-di-da, we have Diamond, we have all these new things. Everybody wants to have a workshop, ideally once a year. We're gonna drive people crazy, so we need to be smarter than that. And I wonder whether you have any ideas.
No, I fully agree. Like just having like this workshop in Argentina and now this one, like it's just really hard to organize those things.
Yeah.
and also to participate. I think like clustering the workshops, having a joint time together, and then having separate times in your favorite communities, maybe this is a way forward. But I fully agree we should be smarter about coordinating these workshops and planning them.
Andy, I have a bit of a sarcastic question. I'm about to blow 100 million core hours on downscaling the 10 CSM2 large ensemble members across CONUS. Are you telling me not to do this?
I would say like we should talk, just because like we spend a lot of time in improving the simulations and you using Wolf. So let's have a chat and like be sure that you benefit from what we did and we benefit from what you do.
Hello. Yes, there we go. Oh, sorry. Yeah, I remember a boundary layer meteorology conference a while ago, and I remember they were examining PBL and groundwater interactions, and that really showed up in areas that had very big terrain differences. So I could see if you could somehow parameterize that based on, you know, the standard deviation of the terrain. But you're talking about in the Midwest, and maybe that's just still enough you know, terrain differences so that you can get some of the groundwater in different places to interact with the, well, with the boundary layer, and then the temperatures are affected and so on. Yeah. Yeah.
So like we know that there are a couple of land atmosphere coupling hotspots.
Right. Right.
Like the Central US is definitely one of those. The boundary layer, it had an effect, but not really a lot. If you don't get the main process of the shallow groundwater tables, you just have too little moisture to work with. So you basically run into a dry climate in this region. Is this the question that you asked?
Yeah. No, that's fine. My sarcastic comment was, so are you saying here that land is really the most important thing and the atmosphere is just a well-mixed boundary condition for us?
So I have to say, like what we do here is, like we do reanalysis downscaling. So we have perfect boundary conditions over a region. And I really have to say, like most of the biases that we see in the simulation are coming from the land atmosphere coupling in winter and in summer. Like the biggest improvement we made are by improving the land surface scheme. And this had the biggest impact on our close to surface. And not only that, even precipitation, climatology. Land is important, yeah.
My best. Good grief. Do y'all ever feel like the more you see, the less you know? I got it. We're on it. Okay. Well, I can tell you right now, there's a reason we have stopped downscaling to 3 kilometers, that figure on the right, and it is because of the value subtraction in dynamical downscaling due to inherited GCM biases. And what I'm going to go through today is I'm going to talk about how some of those GCM biases translate into downscale precipitation biases, specifically in dynamical downscaling. And I like to say that bias correction is this lovely fruit of climate projection synthesis. It's a necessary evil, perhaps. Dave Pierce likes to say, the more you need it, the less useful it is. And the idea behind bias correction is that we fit the statistics of a simulated variable to that of some historically observed reference data product. So it's hocus pocus, really. Excuse me, different bias correction techniques accompany during different downscaling techniques. And for me, I'm interested in physical interpretability to bias correction. And so a lot of these statistical approaches, whether it's QM or multivariate methods, you can end up with weird artifacts in the end product. So today, again, I focus on the impacts of a mean state bias correction applied to dynamically downscaled CMIP6 GCMs. I'll get to that in a moment. But typically, whenever this approach is applied, it's applied in pre-downscaling. And it makes use of a mean state bias correction as well as a variance scaling, although that latter effect has been regarded as negligible, has been found to be negligible.
Specifically, we have dynamically downscaled 9 CMIP6 GCMs across the western US, several of those to convective permitting scales, which I don't present any of those results today. Specifically, though, I'm going to focus on the 9-kilometer grid up here across western North America. And specifically for each one of these GCMs, 2 simulations are downscaled. One with the mean state bias correction applied, and a second with just authentically downscaling that GCM. And this might become important a little bit later as you think about some of these results. We spectrally nudged on the 45-kilometer grid, but not on the 9-kilometer grid. We stayed away from nudging moisture, and that's the point that might come back as you think about this. And we're going to begin by comparing the simulated results to SNOTEL sites across the western United States. So in the interest of time, I'm going to skip this slide here, but bias correction of the mean state effectively boils down to decomposing your reference time series and your GCM time series at each grid point, at each level, into its mean plus a perturbation quantity. And then you basically substitute, you say that your bias corrected signal goes as the sum of your reanalysis base state plus the GCM variability, the subdaily synoptic variability. And we apply this bias correction following the Briere et al. Method from the mid-2010s to these 8 variables here. Okay, let's get right into some of these juicy results. To orient you, we're looking at a SNOTEL site average mean across the western US from more than 700 sites. The blue curve, or the figure on the left is for cumulative water year precip, and the panel on the right is for snow water equivalent. Again, these are the 9-kilometer grid results. And the blue line is the 9-member ensemble mean for the non-bias corrected experiments, whereas the red curve is the same but for the bias corrected experiments. And immediately we lead off by noting that compared to that black solid line, which is the SNOTEL site mean, the ensemble spread, as well as the mean, is they're much larger. Specifically, the non-bias corrected experiments are characterized by a wet bias, both in precip and SWE, and a larger ensemble spread compared to their bias corrected counterparts. Now, you may be saying to yourself, oh, hey, look, the SWE across the western US is pretty low biased after you bias correct, but we have found whenever we've dynamically downscaled to 3 kilometers, that pretty much takes care of the problem. And I just want to point out that these biases get much larger regionally. We're talking about in some of the worst performing GCMs and regionally 65% wet biases, which are eliminated whenever we simply bias correct the mean state prior to downscaling. Now that's the mean. What about the extremes? Well, I don't like this figure. I'm figuring out a better way to represent it, but we looked at RX40 and RX1 days and several accumulation windows in between to find that this wet behavior in the non-bias corrected experiments is basically prevalent for the extreme events as well, whether we're talking about 40-day accumulation windows, 30, 20, 10, etc. Dynamical downscaling as a technique is wetting the GCMs, if you will. However, whenever we bias correct, same thing as for the means, we're drying that solution such that the spread and the means in our downscale projections for all of these GCMs is very close, or more close, if you will, to the parent GCM, as well as our downscale reanalysis and observations. And by the way, I just wanted to point out, this figure here is not for SNOTEL locations. This is actually California state mean. So we should expect a fair bit of comparability in the regional extreme precip, even whenever we're comparing the GCM and the downscale products. Okay, am I doing on time? So the question then becomes why these biases exist in precip. What's going on in the inherited biases that are leading to this overly wet behavior? Because for me, I don't want to give an end user a precip product that has a 400% California mean bias and have them bias correct it, give it to end users and say, hey, use this data, you can trust this. That just doesn't feel right to me. So we're not addressing the bias here with bias correction. We're effectively artificially killing the bias off. But here are vertical profiles across the Northeast Pacific and Western North America. And on the left, temperature bias, middle zonal wind, and then on the right, the meridional wind. And there are several items here that jump out immediately. First, I want to direct your attention to the colored curves. Those are the GCMs we chose to downscale. We carefully selected these based on their how well they simulate Western U.S. and Northern Hemispheric climate. And then the black line here, the black solid line, that's a CMIP 6 ensemble mean, and then the spread is denoted by that gray shading. And immediately, I can just name off 5 or 6 different biases here. I didn't show moisture here, so neglect moisture here. But we see biases in vertical shear, and in the zonal wind, and in temperature, and in the low-level lapse rates that can all favor a wetter solution if not bias corrected out. And so what we did is we've gone through and looked at these biases systematically. So on the y-axis here, I've scattered tropospheric temperature bias from each one of these GCMs against on the x-axis precip bias, downscale precip bias relative to prism. And what we can see is there's a fair correlation between how cold the bias is on the y-axis with the downscale precipitation bias, perhaps expectedly. Then we look at low-level instability. Same thing. Now, we're looking on the y-axis not at the GCM bias per se. We're looking at the difference between the non-bias and the bias-corrected experiment. So when we look at moisture, which, again, moisture is not being nudged. Hopefully, it's being treated more or less internally to WRF. We do actually see, as the model difference wettens, we do see the precipitation bias go up. But then, again, this is a bit nebulous to compare because of how the moisture is being treated internally to WRF. Interestingly, and I just want to note this, when we looked at how these precip biases correlated with winds, we found a very low correlation. So these biases are being driven by the thermodynamic biases in temperature, in the vertical profile of temperature specifically. So a few items. One, bias correction, different from a lot of these statistical bias correction techniques, gives us a physically interpretable result, specifically in those thermodynamics, those thermodynamic figures I just showed. And the way I'm thinking about this is that the GCM is an overly smooth ball that you really have to give, and you're giving its, well, let me think about how to word this. I have it written down here. These GCMs are not adequately resolving the surface forcings that are necessary for precip. So if you let them integrate for long enough, they do integrate their own internal climates that can be characterized by large biases. And once you give these biases to a GCM that has more realistic surface forcings, boom, you get a wetter solution. And I don't know why these biases seem to be systematic in CMIP. We just showed that ensemble mean curve there. This tropospheric cold bias and these low-level instability biases, they seem to be pervasive throughout, at least in this part of the world, in the CMIP 6 ensemble mean. Now, there is some suggestion that our results here are regionally dependent. So I just noted a moment ago that the winds we have found to be relatively unimportant. Those wind biases seem to be unimportant. However, we do find across the Pacific Northwest, which is characterized by the largest biases in precip, thank you, that the wind biases, we do see a positive correlation between the zonal wind bias throughout the deep layer and the downscale precip bias. Now, I just want to finish on this. Why do we care? I just showed you 1980 to 2010 downscale GCM comparisons. Well, we don't downscale GCMs to get at the historical climate. We do it to get at the future climate. And so I want to direct your attention to that upper right figure there. You're looking at the difference in linear trends between the bias-corrected ensemble mean and the non-bias-corrected ensemble mean. Red areas on that figure are showing areas where in the bias-corrected experiments, we're getting a warmer trend than the non-bias corrected experiments in the ensemble mean. And we can see particularly across this high terrain that we're getting like a degree more of warming in the bias corrected experiments than in the non-bias corrected experiments. And this is due to the model's overly wet behavior. We're not melting off snow like we should due to transient warming from 1980 through 2100. And that manifests as a dampened trend in the non-bias corrected experiments, or an accelerated or enhanced trend in the bias corrected experiments. So anyways, I think I did decent on time. Thank you all for your time.
Yeah, thanks. Nice talk. So, two things actually, and hold me honest on this one, but I think you said the wind biases didn't matter much in what you looked at, right? So I didn't want to mischaracterize you, but thinking back to the conversation we had a little bit from Andreas's talking earlier, you know, I think there are certain communities who might find that the wind biases are really important and impactful, like you get into the ET estimates and the flux exchanges at the surface. So it kind of comes back to this interdisciplinary act, you know, and when we're all guilty of this, we're all modelers and we get fixated, we're modeling MCSs or whatever, and sometimes we don't think about the land surface. So maybe I found the previous conversation leading up to this interesting. The other thought you triggered as we look at finer and finer resolution modeling, you know, I think we're a room full of modelers, but how do we truth our data and how do we understand the processes and represent them better in models? So I know as we look at, you know, in some of the work Andreas showed, for example, from here at NCAR, you start looking at these really fine, say, maps of precipitation, and you start looking at observations like PRISM or GridMet. I'm not sure which is truth anymore. So what are our observations? Where are we getting them from? We know rain gauge is undercatch, for example. So the other point, I guess, is, you know, in this paper from Jessica Lundquist, right, about mountain hydrology, and are the models outstripping the observations? So the question, I think, as a community we might chew on, maybe you have some observations based on your work, but what do we need and what are we missing and what's good enough and what isn't from the observational community? Because we need the data to truth our models, we need the data to understand the processes, and we need the data to represent them better in our models. So anyways, any thoughts you may have on that? Sorry for the long question.
No, that's a really good, there's so much to unpack there, but I think one of the things that we've tried to do is incorporate not just in situ products in the model evaluation, but also explicit gridded products. So like, for instance, in the instance of California extreme precip, which I showed earlier, and also on the x-axis of these plots here, the bias is quantified against PRISM, whereas previously we were comparing the bias against SNOWTEL at mountainous sites. And I think the trick is not to get the model to match the SNOWTEL curve or the PRISM curve exactly, it's to get it within that observational uncertainty A. B, your model better not be off by 300%. Just saying. That's like a 0th order requirement. And in some of our initial testing, like, let me just put it this way. I've thrown out, like, just literally gotten rid of, like, 3 dynamical downscale projections, like, that were millions of core hours each, because of, they had, like, 300% snow biases. And then I was told that that's normal within the downscaling community, and I'm like, well, why are we downscaling, you know? So that's whenever I made the call to, you know, stick to, stick to 9-kilometer downscaling, because it's not as computationally expensive. B, just more get my model within the ballpark of obs, because it should be in the ballpark, right? Shouldn't be an order, you know, a factor of 3 to 5 off. So I don't know if that really answers your question. You.